So students, lecture of solids and fluids is loading. So that was actually an elastic behavior of solids, right? Okay, expressed into the very different way. Okay, so again, thanks for your response and the love that you always used to shower on our videos. Thanks a lot, everyone. Right? So, hello, bacho. Sat Shri Akal and namaste from my side. How are you all? So this is Indrajeet Singh welcoming you all to the most sensible platform for an aspirants, those who are preparing for, right, competitive examinations like JEE, NEET. SPW's box of surprises, we are growing high, right, and lots of domains are adding into a surprise box. Okay, so champions, we started this series, right, with units and measurement. Right now it follows, right, it was followed by a motion in 1D, motion in 2D, right, and then we moved on to an NLM, right. Then we saw the concepts of this work, energy and power, followed by rotation, gravitation. Finally we are on solids and fluids. As you all are aware of, this is JEE NEET Crash course, right? So I've combined these two topics, right? These two chapters I've combined, and we're going to see some of the important concepts, right? Okay, those important concepts that holds, right, the weightage, right, from a NEET or JEE point of view. We're going to see that, right? And we are going to clear all of those concepts, right? So my request to you all, so please stay till end. Watch this video till end. I guarantee, right, I guarantee, okay, physics will be really simplified, right? It will be really simplified, okay, and obviously you're going to gain something while attending this lecture. Okay, so today we'll discuss about solids and fluids, right? Now what actually it is, right? As usual, we are going to move on, first of all, as our tradition, right, we are going to move on to the flowchart of this chapter. After that we'll see these concepts, right? See, the number of the topics we are going to see today is, first, it is Hooke's law. Second, we are going to move on through the Pascal's law and its respective applications. We are going to deal with an Archimedes principle, equation of continuity, Bernoulli's principle and its relevant right, applications like Venturi meter and Torsley's law, velocity of efflux and everything, rise of the liquid into the capillary tube, concept of viscosity and the Stoke's law, right? This all things we are going to see today, right? And this thing will be represented, right, into the most simplified form. It will be represented with the help of the visualizations, right? Okay, so first of all, let's move on to the flowchart of those respective chapters, right? If I'm talking about the solids, right, so solid starts with stress, right, and strains. The n number of stresses, we are having n number of strains, right? Okay, we have gone through the types of stresses and strain, right? Okay, we have seen thermal stress, right, compressive stress, tensile stress, shear stress. For this we are having respective strains, linear strains, longitudinal strains, right? Okay, volumetric strains, right? With respect to this stress, we are having the strains, right? The most important thing into the solids, and that is all about the elastic behavior of the solids, right? Elastic behavior, right, of solids, right? Elastic behavior of the solids. Apart from this, the most important stuff goes to, right, on the top of the priority list, right, okay, we can place Hooke's law, right? Hooke's law, it's stress-strain curve, the most important part, right? With this, okay, graph, okay, combination of springs, the relation between spring constant and the Young's modulus, right? These things are quite important from the exam point of view. And after that, right, obviously we are moving forward, right, to the Poisson's ratio eta, right, applications like buckling, bending of a beam and everything, right, and some of the spatial cases. So this is an actual right flow chart, right, of solids. So I'm moving aside on the countdown of 5. Yeah, right, you can have a snap of it. 5, 4, 3, 2, 1. That's it. Let's move on to the flow chart of a fluid, right? Fluid. Right. Fluids, right, starts with pressure and density. Solid starts with the difference between pressure and stress, right? Fluids starts with the pressure and density, but we are not moving into that much detail. This is a Pascal's law. The first one, it is a Pascal's law, right? In the Pascal's law, we are having the equation of the Pascal's law, right? Okay, it's the relevant application of the Pascal's law, U-tube shape sums, right, into the Pascal's law, pressure at depth, that is P is equal to P atmospheric plus rho GH. This is all about the Pascal's law, right? And obviously, yes, these things we are going to discuss today, right? Okay. After Pascal's law, right, okay, fluids moves on, right, to the Archimedes principle, the law of flotation, right? Archimedes principle, right, then followed by law of flotation, and it moves on to the spatial cases, right, of Archimedes principle, the spatial cases of the Archimedes principle. Okay, now the third part of the fluid moves on to the equation of continuity, right, followed by Bernoulli's equation, and it is followed by its application, the Venturimeter and everything, the Torsley's law, right? Okay. After that, we are moving on to the new part, that is, right, viscosity, right? With viscosity, obviously we are going to deal, right, with the coefficient of the viscosity eta, right? We are going to deal with the Reynolds number, right? We are going to deal with the Stokes law, right? We are going to see that Magnus effect, right, and all of those theoretical stuff, right, the flow of the blood in the human body, the Magnus effect, right, the concepts of aerofoil, right, this kind of the things we are going to see, right? And the final thing moves on, right, to the concept of surface tension. With the surface tension, right, we are going to see concept of soap bubble theory, angle of contact, right, rise of a liquid in a capillary tube, or in another sense, if I want to write this thing into the summarized form, I can write it as a capillary action, right? I can write it as a capillary action, right? So this is what, see, I'm not saying, right, the each and every part of the fluids we have covered up, right, but whatever it is important from the JEE and NEET point of view, as the crash course is going on, right, the topic that holds the, right, maximum weightage into an examinations, right, on researching the previous year's paper, right, so that thing I have presented in front of you all. Okay, so this is what are all about the flowchart of the fluids. I'm moving aside. On the countdown of 5, you can have a snap of it. 5, 4, 3, 2, 1. Now let's move on to the right, the most important concept. See, you all are aware of what kind of the stresses are there. You all are aware of what kind of strains are there, right? Even you know about the types of the modulus, like modulus of rigidity, Young's modulus, right? Bulk modulus, right? Okay, you all are even aware of the Poisson's ratio, right? But the most important thing, right, from the exam point of view, that holds the highest weightage is the Hooke's law, and its respective explanation, analysis, graph, the stress-strain curve, and some of the special cases of the combinations of rod, right? So this thing we are going to see, and with that, the concept of elastic potential energy and the energy density. So these are the list of the prominent topics, right, from which there is a highest probability. You can say highest possibility is there for a sum to come into, to appear, like to come into an examination paper, right? So what actual, right, the Hooke's law states? It's a very simple thing, right? Hooke's law, up to certain proportionality limit. Limit is a part of life, right? Whatever you are doing, right, okay, you are in foundations, okay, you are always in foundations. Physics is only the thing that is not bounded, okay, it is not completely bounded. Physics is only the thing. Apart from that, the entire human race on this earth, or whatever the species exist in the entire universe, are bounded by some laws, right? Bounded. I'm again highlighting this word, bounded. Similarly, if you are bounded by some XYZ laws, right, this Hooke's law is also bounded by something, and that word is up to certain proportionality limit, right? So first of all, I'm writing that stuff, right? Up to certain limit of proportionality. Up to certain limit of proportionality, right, we are bounding this thing, right? The stress produced is directly proportional to strain. The stress produced is, right, directly proportional to the strain. But kindly mark this word. This is an important thing. Up to certain proportionality, up to certain proportionality limit, the stress produced in an elastic object, it is directly proportional to, not elastic object, I must reframe that statement, right? Okay, elastic solid, the stress that is produced in elastic solids, right, is directly proportional to strain. This is what all about the Hooke's law. But up to certain limits of proportionality. Why? Question mark. As I said, physics is all about why and suppose. Why? Right? Even you can see this, right? The visualization in front. This is all about the experiment, right, of a Hooke's law. Okay, something it is loaded into an, let us take an example, a very simple example. If I'm talking about the spring, if mass M is hanged, right, on a spring, obviously it is going to elongate from its natural length, right? Suppose initially this was its natural length, L initial, right? Now this thing, this is the final length of the spring. Obviously it is getting elongated now. So whether Hooke's law is applicable for entire process? No. Right? Is it applicable for entire process? No. If it is a perfectly elastic body, then yes, we can say, right, for entire process of stretching and getting compressed, the Hooke's law is applicable. But right now in this chapter here, we are dealing with the concepts, right, of the behaviors of solids. Not we are, see, that is a classification of perfectly elastic bodies and everything, right? Ductile and brittle and lots of stuff is there. But if we are talking about the solids, right? Okay, if we are talking about solids, then obviously we are going to face some foundations, because they are not, it is not for sure that all solids that exist into the universe, right, they are perfectly elastic. They are perfectly elastic. So that's why, right, it is written up to certain limit of proportionality. I am going to explain this thing into the detail, right, while moving on to the concepts of the stress-strain curve. So don't get worried. Right now we are going on to the Hooke's law only, right, and we are going to see one of the examples of it. Suppose initially the spring is in its natural length. Initially the spring is in its natural length. Now suppose if mass is hung, right, this is A. Okay, suppose we are placing a mass on this spring, then obviously, right, okay, it will so can I say this is the initial length, or you another sense, can I say this is a natural length of the spring, right, and this one is an elongated length, right, this is an L final. What is the difference of the length, right? What will be the difference of the length? The change in length, right, that will show how much amount of the strain is produced. If strain is produced, it means, right, with reference to the strain, we are always having one external force that is doing some kind of a work and producing the stress. So here mg is the force, right, mg is the force that is applied, right, when we place that mask, right, we attach that mask with the spring, right. Mg was the force that was applied into the downward direction, right, and that force was responsible for, right, a stress, and as because of that stress is produced, obviously we are, right, observing some of the configurational changes into the body that shows a presence of strain. So it means stress is directly proportional to strain, right? More stress, high will be the configuration, more stress, high will be the configuration changes, right? More stress, high will be the configuration changes. The less stress, right, more amount of the stress, more will be the configuration changes. Less stress, less strain. Now removing this proportionality sign, what we get, right, okay, removing this proportionality sign, right, we are getting, okay, the new constant, the constant of proportionality, that is known as Young's modulus. The constant of proportionality, that is known as what? Young's modulus, right? This is a constant of the proportionality. In another sense, right, I can define Young's modulus, or I can generally define the modulus as ratio of stress by strain, right? I can generally define, right, the modulus as the ratio of stress and strain. Modulus as the ratio of stress and strain, right? So this is what all about the Hooke's law. What actually the graph is, what actually the stress-strain curve, what is an actual meaning of up to certain proportionality limit. Okay, let me give you all a hint about it, about that word, about that statement, the small, that is up to certain limits of proportionality. See, suppose M was attached, right? We saw we observed the change in length into the spring. Now let's increase the mass. Suppose if 2m is attached, right, more amount of the stress will produce, more amount of the strain we are getting. Let us take an example. If we are attaching 3m, the more amount of the strain will produce, stress will produce, and that will result into the, right, getting the more amount of the values of strain. Now suppose if 10m is attached, then what, right, we are going to observe how things will go on. Is it for sure, right, that this spring is going to elongate on attaching the mass of 10m? Question mark. Now students will have students will be having, right, the things into the mind. Sir, it completely depends on how spring is. Let's compare this thing to the day-to-day life. It completely depends on the nature of the human, right? It completely depends on the nature of the human, that how he is reacting to the problems. How much amount of the patience he holds. Patience. Same. It completely depends on the Y value. It completely depends on how string is, right? If I'm talking about the spring that we are removing from the ball pen, it is not having that much capability even to we can attach the 100 gram of mass with it, right? On attaching the 100 gram of a mass with that spring that has been removed from the ball pen, right, it is going to get deformed. Right, so there are some certain limitations, right? Now, if I'm talking about a spring that is used, right, into the bikes, in other words, the springs near sockupsers, if you have heard about, right? So those are what we can say, right? Those are like having the high value of the K, right? They can hold the high amount of the forces, right? But as compared to the spring that we removed from the ball pen, right, that is having very less value of the K. So that is a difference that I want to show you all in front. There is a difference. So whether this string is capable to hold the 10m mass or not, it completely depends on the nature of the spring, how spring is, and up to what limit he is able to produce the stress, up to what limit he can change its configuration. Two most important terms, right? What will be the capability, right? Up to what limit, right, the string is capable to hold the mass, up to what limit the string is, the spring is capable to produce a strain, and up to what limit the spring is capable to give the values of strains. Before that, what will happen? After that proportionality limit, what will happen, right? That we are going to see into the graphs, right? So this is all right about the Hooke's law. Okay, so removing this proportionality sign, we are getting Young's modulus, right? And this Young's modulus is a ratio of the stress by strain, right? If it is the volumetric stress produced with respect to the volumetric strain, then we are having bulk modulus, right? In bulk modulus, we are also having the two classifications, right? Bulk modulus, right, for adiabatic process and for isostatic. That thing we are going to see into the thermodynamics, right? So what kind of stress is produced? Ratio of what kind of a stress that is produced to its relevant strains will give, right, the new constant of the proportionality. If it is a tensile or compressive, then we are saying it is a Young's modulus. If it is a volumetric stress, right, okay, and if it is a volumetric stress and with respect to this it is a strain, then obviously we are naming it as a bulk modulus. So lots of things are there. So this is what the basic idea of the Hooke's law is, right? Okay, now while conducting an this experiment was conducted, right? Okay, this experiment was conducted to to determine the experimental value of that constant of proportionality that is obtained from the equation. For that, one graph was plotted. That graph was stress versus strain graph, right? So if I'm talking about a graph that is stress versus strain graph, right? Stress versus strain. This graph will help us, right, in determining the constant of proportionality, that is Young's modulus. Suppose if we are conducting an experiment, this is the value of the stress and this is the value of strain. For Hooke's law, as the stress is directly proportional to strain, it means when we are conducting an experiment, we are getting its relevant observation, right? This graph should be straight line. In limits of proportionality, this graph should compulsory be the straight line. I use that word into the Hooke's law, na? Up to certain limit. Up to certain limit of proportionality. Up to certain limits of proportionality, this graph, right? I'm talking about that range, I'm talking about that limit up to which the Hooke's law is valid. Within that range, this graph should be compulsory straight line. I am talking about, yes, again I'm repeating that statement. I am talking about the range, a limit up to which the Hooke's law is valid, right? Okay, up to that limit, this graph should be straight line. Before and after, what actually it is, we are going to discuss in detail, right, in the concepts of stress strain curve, right? But right now it should be the straight line and the slope is a Young modulus. Slope, it is the value of the Young's modulus, that is stress by strain. You can see in this visualization, right? Mass is hanged, spring is getting elongated, then up to certain proportionality limit. See, suppose, let's plot this graph in this visualization. Suppose the weight is 10 Newton. For that, we are having the respective elongation. Suppose if we are increasing a weight to 40 Newton, so with respect to this, we are having an elongation. So this will be my first point, right? And this will be my, right, second point. Suppose if I'm increasing a weight, right, to 80 Newton. So for that, we are getting the respective elongation, right? So up to that limit. Now see, 80 Newton is the limit of a spring. Up to 80 Newton you can attach a mass, and after that it will get, whether it will get deformed or it will get loses elasticity, right? We are not aware of what is going to happen, but we are only aware of our foundations, right? That limit of proportionality, that is 80 Newton. Up to 80 Newton we are having the graph like this way, right? After that, what will be the nature of the graph, right? We are not aware of. So that's the up to certain limits of proportionality. Okay, so the slope of stress versus strain graph, right, always gives its modulus, always gives its constant of proportionality. Okay, now let's move on to the stress strain curve, and to understand the stress strain curve we need to take one example, right? Okay, by showing that we are going to understand that stuff into the convenient manner. Now let's have an example in front. See, I'm taking one spring, right? See, one rigid wall is there, right? I'm having a spring of spring constant K. Initially no force is applied, right? Initially no force is applied. Can I say here, right? No force is applied. Right. no force is applied, right? If no force is applied, it means it is a very simple thing, right? We are not going to see any kind of an elongation or compression, right? So can I say no elongation, no compression, right? No elongation, no compression, no force is applied, right? In first case. Now suppose let us take an example, right? If we are applying the F amount of the force, obviously the spring will get elongated from its natural length, right? Spring, okay, just a minimal amount of the force, right, we are applying, then spring is getting elongated from its original length, right? So we are facing an elongation, okay, great. So while plotting the stress strain curve, right, initially, right, while plotting the stress strain curve, initially everything was at 0, right? Now I increase the value of the, right, forces F, right? Then we got the relevant strain to that. So the graph is like straight line, right? Now I am increasing the value of F, right? Again, increasing the value of F, then we are having the more elongation. Suppose this is a new value of a strain, that is its limit, and this is a new value of F dash, right? This is a limit up to which, right, I can apply the F, right? It doesn't mean that external force is bounded, that then he can or it can only apply the value of F dash. No. Even you can apply your even you can apply your 1000 Newton, right, whatever you want. But there are some limitations of this spring. The spring can hold only up to the value of F, and that it's a limit of proportionality. Up to the maximum limit of F dash, this spring can elongate, and it has tendency to come back to its original position. It has tendency to come back to its original position. It has tendency to come back to its original position. Source is rigid, right? It is rigid in nature. Now he applied the 4 times F dash value or 8 times F value, whatever. It will be a large amount of the F. Beyond this, the spring will lose its elasticity. Beyond this, the spring will lose its elasticity, right? Beyond this, spring will lose its elasticity. Suppose if more than, right, if we are applying the value of the force that is more than F dash, right, the spring will lose its tendency to come back to its original position, right? Now we are crossing the limits of proportionality. You can see this example, right? This was the section, this was our limit of proportionality. Up to this, Hooke's law holds valid. And we are getting the graph as a straight line. Beyond this, first step, object will lose its elasticity. Second step, if still we are applying the force, right, after the object has already lost its elasticity, then occurs the deformation, right? If I'm talking about a simple spring, let us take an example. I'm having one spring in my hand. I'm showing you all in front. So you can see this spring, right? This spring, right? If I'm trying to apply a force, right, the spring will face an elongation, but up to certain limit, right? Up to that limit, right? The force is applied up to certain one specific limit, right? If the force is applied, the spring has tendency so that it can come back to its original position, but beyond that, spring loses its elasticity. So beyond that, if spring loses its elasticity, it means we are crossing the limits of proportionality and Hooke's law fails. Within the limits of the proportionality, the spring has tendency to come back to its original position. Hooke's law is valid, everything is fine. The graph is a straight line. Now, this is the fourth step. Beyond this, the spring has lost its elasticity. Again, now, right, okay, we are applying the value of the force, and that is value is like quite high. And there occurs the fracture point. Okay, these things are only important, right? Beyond this, right, lots of things you can see like ultimate strength and yield and everything, right? Ultimate strength is a point, right, between the object when it's it is, right, the ultimate strength is in between, right, the point in between the fracture point and a point where the spring loses its elasticity, right? Okay, lots of things, right, into the thousands of resources it is explained into the different way, but right, in the entire topic, this thing is only this much amount of the things, right, are only important, right? Okay, up to, so this is what all about, na? I told you all, na, this one, up to certain limits of proportionality. That limit of proportionality is for an elastic object, right? Right, we are having this boundation. For an elastic object, we are having this boundation. What kind of a boundation? Up to limit. Up to what limit? Up to the limit, right? Okay, till this object will have a tendency to come back to its original position, else things will go weird. Hooke's law fails. So this is all about the stress strain curve in final, right? If the source is not stopping, right? Okay, if this force applied value will not become less, right, or whatever it should be, right, the object will get fractured. So whenever we are dealing with whenever we are dealing with the elongation and the compression into the spring, right, see, let us take an example. If this is a spring, on application of the F force, right, the spring is getting elongated. On application of, right, X force, right, the spring is getting elongated, right? And for this elongation of the spring, right, up to certain proportionality limits, right, one restoring force is generated, that is Kx. This restoring force, what actually it do, right, it will help, right, an object to regain its original position on removal of this external force. Right, so see, whenever an external force is applied, right, work is done. Now this work is done, obviously it is against the restoring force. We are applying the force, we are facing an elongation, right? Obviously the work is done, and whatever the amount of the work is done, right, somewhere the Kx, the restoring force, is involved. For this, right, Kx, the restoring force, this is a conservative force, right? This restoring force, it is the conservative force, and whatever, right, the work is done for the conservative forces, it is always stored into the form of the potential energy. If mg does the work, it is stored into the form of the gravitational potential energy. If Kx is doing the work, right, or it is against, right, whatever it should be, it is stored into the form of the elastic potential energy. So here, whatever the work is done, it is stored into the form of the elastic potential energy, right? And you have seen the derivation, right, relevant to it, and that is U is equal to half kx square, right? And we got this derivation by dw is equal to f dot dx, replacing the value of the x as minus kx dx like that way, right? We are getting the potential, the elastic potential energy, right? Whenever the spring is facing an elongation or compression, there is always an energy stored inside it. And we are naming that energy as the elastic potential energy, and its relevant equation is this. Obviously, it is a scalar form. Apart from this, if I'm talking about a three-dimensional object or any elastic object, we are sure that if work is done, energy is stored. But what amount of the energy that is stored per unit volume of an entire object, right? What amount of the energy that is stored per unit volume, that shows the example of the energy density, right? That is equal to half stress into strain, right? Okay, and that energy density is energy, right, per unit volume. Lots of formulas are there, right? You can make it out replacing the Hooke's law, right? You can make out, see, suppose if I'm talking about a Hooke's law, right? See what we got, the stress is directly proportional to strain. Okay, so sigma, that is equal to y strain, sigma, that is equal to force per unit area, stress, that is y delta L by L, that is a relevant strain. So value of the y is FL by A delta L, right? If you are replacing this Hooke's law, right, if you are replacing this Hooke's law, right, into the relevant equations, right, then we are getting the new outputs. If we are replacing the Hooke's law into the equation of the energy density, then we are getting the new outputs, right? Okay, it doesn't mean we are going to change our base. The base is that energy density, it means energy per unit volume, and we can define it by the respective formula, right? Now, lots of formulas are, as you all are aware of, right? Now, there is a relation between the spring constant and the Young's modulus, and that will help us, right, to understand the concepts when the springs are connected in series, how to determine the equivalent K, and when the springs are connected in the parallel, how to determine the value of the K. So first of all, we are going to see the actual relation between the spring constant and the Young's modulus, and then we are going to see some of the cases of the combinations of the rods when they are considered as the springs. So spring constant and the Young's modulus. See, suppose if, right, F is applied to an object, then we are having the value of the restoring force, right? So according to the Hooke's law, can I say force that is acting per unit area, that is equal to Young's modulus delta L by L? Can I replace this value of the force as K delta L, and that is the restoring force is Y delta L by L? Delta L will get cancelled. We are getting the constant of proportionality is YA by L. That is an actual relation of a spring constant, right, and Young's modulus. That is an actual relation of this spring constant and the Young's modulus. And this relation we are going to use, right, in determining, right, the new results, right, when springs are connected in series and they are connected in parallel, right, when springs are connected in series and they are connected in parallel. Combination of rods. Combination of rods. See, this kind of the sums, right? Okay, they are already asked in an examination, right? Okay, the sums based on this concept, right? Okay, I'm going to show you some PYQs also based on it, right? But first of all, let's move on to the actual, right, concept, right? Okay, let's see this thing from the ground zero. what will happen? Right, let us take an example. This is one rod. This is the second rod. This is a rod made up of the steel material, and this is a rod made up of the brass material. If weight is attached to it, so my question to you all is whether we are going to face the elongation or compression in it or not. Obviously, we are going to face some compression or elongation in it. Yes. But how to solve this kind of the sums? Let us take another example. Suppose if two rods are attached like this way. The first one is steel. The second one is brass. And mass attaches to it. On attaching the mass, whether this rods will phase or elongation or not. Right, whether they will, whether we are able to observe the elongation in the objects and the solids or not. To solve this kind of the concepts, always keep one thing into your mind. That is, always see, we are saying the elastic behavior of the solids now, right? Then it is wrong to consider this solid as an individual spring. We can consider it because we are understanding the elastic behavior of the solids. To understand it into the appropriate manner, yes, we can consider that part as a spring, right? So always consider, this is only the way to understand these sums. Always consider, right, the rods as springs. This is the best analogy, right, to understand this concept. Best analogy to understand this concept. Right. Now, how the things will appear in front of me? Right. How things will appear. First case. This is a spring that is made of some material. Right, this is another spring that is made of some material, but I can't say it is having some Young's modulus, but yes, I can say this spring is of the spring constant K1 and this spring is of the spring constant K2. I can't say it is made up of this material, but yes, I can determine the value of I can give the value of the K. Even I can correlate the value of the spring constant with its respective modulus. Right, so we can, right, with that value we are able to identify of what material this spring is made. Right, so this is an indirect explanation to understand this concept. Right, if rod is there, we can consider it as an spring. Right, this is an analogy to understand this concept well. Second, if they are connected in series, it's okay, no worries. This is a spring of spring constant K1. This is a spring of spring constant K2. Right. Right. So there might be, if these two things are connected, right? So there might be some effective spring constant that will produce the same result as these two springs are giving. Here also we are having the value of some effective constant and it is giving the same result as these two springs are giving. That thing, this would be our next step to determine the formula of this K effective, right, and to compare it with the concepts of the Young's modulus, as this solids are elastic. They are showing an elastic behavior, right? So first of all, I'm sorry, I am extremely sorry for that, right? Okay, yes. If springs or rods are connected in series. Springs or rods. Suppose this is a rod, right, that is having Young's modulus y1. This is a rod having Young's modulus y2. Mass m is attached. Can I compare this analogy to the springs? Right. This is the first spring that is having spring constant K1. This is a second spring, right? Mass is m is attached and this is a constant K2. Now as they are in series, right? Okay. The elongation into the first will be delta L1 and elongation into the second will be the delta L2. So what will be the resultant elongation? That is delta L is equal to delta L1 plus delta L2. In springs, right, elongations of the springs, right, those who are connected in series are different. The force applied on them is same, right? The elongations are different. So in this case, what we are going to get? Can I say according to the Hooke's law? Right? Force per unit area stress is equal to Y delta L by L. Can I say delta L that is equal to FL by AY? Right? So if I'm talking about the resultant, can I replace this equation and can I consider this is equation number 1? Yes. Can I consider this as equation number 2? Replacing 2 in 1. Replacing 2 in 1. So what I'll get? F into L equivalent whole divided by area into Y equivalent, that is F into L1 whole divided by, right, area into Y1 plus F L2 whole divided by area Y2. It's A equivalent A1 and A2. This is the general formula. Now suppose area of the cross sections of both are equal. If A1 is equivalent to A2, right, and even F is constant in both, then finally we can write this equation as L equivalent by Y equivalent, right, that is equivalent to L1, right, this one, L1 by this one, L1 by Y1 plus L2 by Y2. Suppose if we are keeping the value of the F as like this way, right? Now if F is getting cancelled, then we are getting the, right, equivalent, Y equivalent, right? We are getting this Y equivalent, right? Now suppose if we are replacing the value of Ka, right, K as Ya by L, right, in this equation, right? So finally we are getting the K equivalent as K1 K2 whole divided by K1 plus K2 when springs are connected in series, right? So this is how the things are resolved, right? Okay, this is how the things are resolved, right? Can I replace Y as Ka by L? Yes, Ka by L. Obviously the area is going to same, so things will get cancelled out, right? And we are getting the final equation as this way. Now suppose if strings are in parallel, we are not moving on to the right derivations of it, but we are having the final equation. If strings are in parallel, this is the value of the K equivalent or K effective, right? Because in parallel, right, force are getting divided, right? Force are getting divided always, right? Okay, so this is a new concept, right? Sums based on this are already asked into the NEET 2019 and 20 paper. We are going to see that stuff also, right? Okay, and the final part, this is a thermal stress, right? This thermal stress obviously we are going to see into the, right, heat transfer also, but I'm going to show you all. Suppose these are the two rigid rods, two rigid walls, right? And in between the two rigid walls, obviously one rod is connected. Between the two rigid walls, one rod is connected and continuously heat is supplied to it. On application of the heat, see, you can see into the visualization, when heat is applied to the fine ceramics, right, obviously it is, we are observing the change in length of it. So thermal stress is what? Stress as of a simple term, thermal energy. Stress as of the thermal energy, right? Again, if we are defining it as a stress is equal to Young's modulus of strain, that is delta L by L, right? Okay, now consider this is equation number 1. According to the concept of expansions in solids that we are going to see into the next chapter, right, we can use this equation, and if I am replacing this value, I am getting the thermal stress as Y alpha delta T, right? Stress is because of a mechanical force, we are defining it as a tensile compressive. Stress as because of any kind of the thermal energy, right? Okay, then we are defining it as a thermal stress. It's a very simple thing, right? Don't worry, we are going to see that stuff into the heat transfer also, because at this position of the time you are not aware of how this equation we are getting, right? How with the expansions, right, lots of things are there, right? Lots of ways are there, right, through which the solids will get expand, right? Okay, now let's see some sums related to the Hooke's law, right? Okay, now the stress strain curve drawn for the two materials. We are drawing the stress strain curve for the two materials. This is for the material X, right, and this is for the material Y. This question is asked into the Odisha NEET 2019, right? It is observed that ultimate strength point and the fracture point are close to each other. Ultimate strength point, it means this is an ultimate strength point and this is a fracture point. We have seen this stuff into the stress strain curve. Ultimate strength point, USP. This is the fracture point. For X, it is nearer. For material X, but far apart for material Y. For material Y, this is a fracture point and this is an ultimate strength point. For X, they are nearer. For Y, they are far. What kind of the object it is, right? What kind of an object it is? It's a very simple thing. The first one is a brittle and second one is a ductile. The distance between, right, if the USP and the fracture point, the ultimate strength point and the fracture point are quite nearer, it means on application of an force that object is easily breakable. It means it is brittle. If these are far away from each other, then obviously it shows the ductile behavior. So X is brittle, Y is ductile. See, based on this stress strain curve, the question is asked into the Odisha NEET 2019. See, Karnataka NEET 2013, right? We saw this sum, right? The combinations of rods, right? Let's see this. If the ratios of the diameters, lengths and Young's modulus of the steel and copper wires are shown into the figure. See, ratios of diameters, lengths and Young's modulus are P, Q and S. Diameter D1, D2. Ratios of the diameters, right, are P. Lengths and Young's modulus L1 by L2, that is ratio is Q and Young's modulus ratio is S, PQ and S. Then corresponding ratio of their increase in the length would be what? Corresponding ratio of increase in length, delta L1 by delta L2. According to the Hooke's law, right, I'm writing this term according to Hooke's law. Can I say force per unit area, that is equal to Y delta L by L? So delta L, that is equal to FL by AY. Right? Can I use this equation? Yes, I can use this equation. Can I consider steel as number 1? Can I consider copper as number 2? For copper, the force is only 5 mg, but for steel, the two blocks are attached. It is 5 mg plus 2 mg, it is 7 mg. For copper, this 5m is only applying a load, but for steel, right, 5m and 2m both are applying the load. So can I say for steel, delta L1, that is equal to, sorry, seven mg into L1 by area can we replace it as a pi d square by 4, right? Can we replace the area of the cross section as the pi d square by 4? Yes. It is into 4 by pi d1 square into Young's modulus of y1. For copper, we are having delta 2 Se. It's 2m and it is 5m, right? So for copper, we are having the 5 mg, right? So it is 5 mg, right? Okay, into this is L2 into 4 by pi d2 square, right, into y2. Can I take the ratio of 1 by 2? Corresponding ratio of increase in their length would be, right? Okay, then we are having, right, delta L1 by delta L2, taking ratio of this two equation, right? I think it will be 7 L1, right, by d1 square y1 and into phi L2 into d2 square by y2. So delta L1 by delta L2, that would be 7 by phi L1 by L2 y2 by y1 d2 square by d1 square, right? So delta L1 by delta L2, 7 by phi. L1 by L2 is q, 7 by phi of q. Y1 by y2 is s, so it is divided by s, p square. So this will be our answer, 7q by phi p square s, right? 7q by phi p square. This, right? So this is how, in this also, right, the combination of rods are asked, right? Okay, the things are there, right? And these are also helpful from the JEE point of view. A wire of length L and the area of cross section. See, this question is asked, it's a very simple question using the Hooke's law. It is asked in NEET 2020. A wire of length L, area of cross section A is hanging from a fixed support. Wire of length L, length is L, area of cross section is A, is hanging from the fixed support. The length of the wire changes to L1 when M is suspended with its free end. Suppose if M is suspended, right, the new length we are getting as L1. The expression of the Young's modulus is very simple. Hooke's law. According to Hooke's law, right, according to the Hooke's law, right, Y delta L by L is equal to force per unit area, right? Okay, so can I say it as what? Force is mg, right? Force acting is mg, right? What we need to calculate? We need to calculate the Young's modulus. So Y is equal to FL by A delta L. F, that is mg L. This is an original length, this is area. What will be is change in length. Initially the length was L, the final length is L1. Then obviously the change in length we are going to get L1 minus L. Replacing it here, finally we are getting it as MGL whole divided by area L1 minus L. Right? The fourth is the perfect answer for this specific question. When a block of mass M is suspended, see this question is asked in NEET 2019. When the block of mass M is suspended by a long wire of length L, the length of the wire becomes L plus L. The new length becomes C. Initial length, that is equal to L. Final length, it becomes L plus, right, L. Okay, sorry, initial length is capital L. So what will be the change in length? Del. From this equation we can define it as NL. What is an elastic potential energy stored into the spring? Right. So what is the formula of elastic potential energy? Right, elastic potential energy. Lots of formulas are there, right? Lots of formulas, right, are there. So can I say it as a half, that is stress into strain? Can I say it as a half kx square? It's prior to use this formula. It is half kx square, that is half force into x, right? And finally we are getting it as a, right, the elastic potential energy as a half, force is mg, right, and we are having it as a L. So the elastic potential energy stored, that is mg L by 2. So students, let's move on to the next topic, that is Pascal's law and its application. In solids, the most important stuffs, right, related to the, right, like from the exam point of view, right, we have seen all of that part. Okay, now we are directly moving on to the, right, this fluids part. As I told into the beginning of this session, right, the most important topics related to the solids and fluids, right, we are going to see. Okay, now Pascal's law and its application. What does the law states, right? How we are going to derive that stuff? Okay, lots of things, lots of right, derivations are there, right, and lots of sums are already asked into an examinations, okay, related to it. So here, from here, right, the fluid is going to start. But before moving on to that part, I want to clarify what there is one difference between solids and fluid. In solids, we were continuously dealing with stress, but in fluids, right, we will deal with the pressure. Dimensionally, stress and pressure, they both are same. Dimensionally, stress and pressure, they both are same, but dimensionally they both are same, right? But there conceptually there is a difference in understanding, right? They actual there is a difference between them. Stress means force acting per unit cross section area. Pressure means, we have heard about migraine. Some students are might be having a problem of that. This is a, like, you have heard about that. Okay, in migraine, right, there is only one, what we can see, like, one specific part of the brain, right? A human feels ache, right, in one specific part of the brain. It feels like someone is trying to stretch a vein, right? Someone, it feels like a specific part of the brain, right? Humans always used to feel an ache. That is migraine. That's what we can do. The stress is developed at that position. But in my entire head is paining, feeling an ache. That's a pressure. Difference between stress and pressure. Force acting per unit cross section area. force acting on entire area, that is pressure. Force acting per unit cross section area, stress. Chuck, 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 stress. It's pressure. Okay. So now this was an actual difference because it is needed. This thing needs to be clarified in front. Okay. So now, what does the Pascal's law states? Right? What does the Pascal's law states? It states that whenever a liquid or whenever an object is immersed inside a liquid, right, the liquid exerts the force equally in the all directions, right? It states that, right? Again, I am reframing that statement. If we want to clarify that stuff into the most simplified form, if you want to understand this Pascal's law into the most simplified form, then I'm going to write it here. At any point, right, if pressure is applied at any point inside a fluid, right, at any point inside a fluid, then it is equally distributed in all directions. Right? It is equally distributed in all directions. The best example is sprinkler. The big on spray you have heard about. We are applying at any point on side a fluid. If you are applying a pressure, then it is equally transmitted into the all direction. You can see into the visualization, right? Okay, this is a C. At any point, right, a pressure is applied, then it is getting equally distributed in all directions, right? It is bursting out from all of these holes of the sprinkler. See, yes, that's the thing. That's the Pascal law is all about. In another sense, if you want to understand, right, the Pascal's law into the more convenient manner, let's take another example. Suppose this is the surface of the water. Suppose the object is immersed inside the liquid. In another sense, right, we are applying a pressure to it, and even that pressure is changing with respect to depth. Suppose at the specific depth, right, whatever the pressure this object is applying, it is equally transmitted in all direction from the towards the fluid, right? I think the sprinkler is the best example to understand, right? The sprinkler is the best example to understand this thing, right? Now, see, this is a statement of the Pascal's law, right? This is an actual statement of the Pascal's law. Behind this, there is a derivation, right? There are some of the applications of the Pascal's law, right? Okay, now see some of the best examples, right, in which the Pascal's law is used. Some of the best examples, right, in which the Pascal's law is used. We are going to see that stuff. Piston in engines, right? Piston is that kind of the structure. See, there is one chamber, and always we are having this kind of thing, right? Okay, this is a piston, and there is always a liquid present behind it. If you have seen that ad, Castrol ECG, engine clutch gear, right, you can see that thing that is continuously rotating in that ad, that is piston. Suppose if you are applying a very little force now per unit area to this part of the piston, right, then that force is going to equally distributed on all directions inside the fluid. It is going to transmit equally into the all directions. Second example related to the Pascal law, right? Okay, first, hydraulic brakes. Or the best example of a day-to-day life, hydraulic jack. You have seen nowadays, right? When we used to buy a car in 2014, 15, or in the span of 2014 or 19, then we used to have a manual jacks, right? Okay, whenever what with the tire get punctured, right, and we need to replace it by the stepney. And what we used to do, we used to place the jack at the bottom, right, and we used to rotate that jack manually to lift the car up, right? We used to rotate that jack manually to lift the car up, and then we were replacing right, the entire tire, right, so that to ease this process. Okay, nowadays the companies are giving the hydraulic jacks. Some of the companies are giving the hydraulic jack. It is very easy. You have to just apply a little pressure, is equally distributed in all directions. It is lifting up the entire car, lifting the entire car. So what is an actual? In the previous situation, we used to rotate that part manually, right, and the car was getting lifted up. But here, in the case of the hydraulic jack, you have to just push a little, just apply the force a little, right? Hydraulic, it means as, right, inside that mechanism, the use of the fluid is there. As because of this Pascal's law, right, hydraulic machines are quite used, right, in lifting up the objects. You have seen the cranes, hydraulic cranes, they used to lift even, right, they are having the capability to lift the tractor also, right, because on application of very little amount of the force, right, the pressure is transmitted equally into the all directions and we are getting the maximum amount of the output. Same in case, see, this is an example of our day-to-day life. A hydraulic jack. Many of the students might have seen also, right? We are just placing the jack near, what we can say, at the bottom of the car, and we're just placing a little. It is having the platform in front at the top, and we're just applying a push like this way. Immediately it is lifting up to the car. So with the minimum effort, right, using this Pascal's law, we are having the maximum output. So this is what is all about, right? Now let's have another example of it. Okay, so let's see this proof of the Pascal's law, right? So for that, let us take an example. Suppose this is a container, right, and this is filled inside the fluid. Now suppose we are keeping one, right, okay, this shape object right inside the fluid. Now we need to prove that pressure acting on this, it is equally into the all directions, right? Pressure acting on this, that is equally into the all direction. It means that suppose this is a side first, then there is a pressure P1. Suppose this is a pressure P2, right? And this is a pressure P3. According to the Pascal's law, right? According to Pascal's law, right? We need to prove, right, that P1 that is equivalent to P2 and that is equivalent to P3. Suppose if this is a theta, right, then can I say that this is a theta? Suppose here the force acting is F1, so can I say that this is F1 cos of theta and this is F1 sin of theta? From this side force is acting is F2 and from this side force acting is F3. Right? Then can I say that first from P1 side, can I say P1 that is equal to force acting by area A1? This is an area of cross section A1, this is an area A3 and this is an area A2. For the second part, can I say pressure 2 that is equal to F2 by A2? As prism is in rest, it means all the horizontal forces will be balanced, all the vertical forces will be balanced. So this F2 that will be equivalent to F of 1 sine of theta. And suppose if this is area A1, right, then this A2, this will be equivalent to A1 sine of theta and this will be equivalent to A1 cos of theta. That's it. It's A1 sine of theta, this sine theta is going to cancel. Then P2 that is equivalent to F1 by A1. Similarly for the third part, P3 that is equal to F3 by A3. But here F3 that is equal to the vertical component of this force, that is F1 cos theta, and area is also A1 cos of theta. Cos theta is gonna cancel. This is also equivalent to. So from this three equation, can we say that, right? P1 is equivalent to P2 and that is equivalent to P3, and thus is the proof of the Pascal's law. Right? This is the proof of the Pascal's law. Right? So again, what it states? It states that at any point if the pressure is applied inside the fluid, the presence of the object, it means pressure is implied. Right? So that is equally transmitted into the opposite all directions. One question. With respect to the surface level, right? With respect to the surface level, how the pressure is changing with respect to the depth. The two most important concepts, right, of the change of the pressure with respect to depth and the hydrostatic paradox, right? These are the two most important one on which, right, actually the questions has been asked, right, in previous years. How? Let us take an example. Suppose this is a water level, right? The surface level, right? With respect to which, right, one cylinder is kept of height h, cross section area A. Between these 2 points of the cylinder, are we having any kind of the pressure difference? Yes. With these 2 points on the cylinder, let us take an example at the surface, right? The P atmospheric pressure is always acting. And one thing about this, it always acts perpendicular to the surface. If surface is tilted at the theta, right, P atmospheric is tilted at the theta. If the surface is tilted at theta, the P atmospheric pressure is always tilted at the theta. So from height, see if I'm talking about the cylinder with the two edge points A and B, the height, the difference between A and B, right, is of h. So between these 2 points, right, whether pressure difference exists or not. Whether pressure difference exists or not. I must say yes. Let's see how. At this point, can I say the pressure acting is PA? At this point, this is cross section area. The pressure exists as PB. Difference between these two, as the object is at rest, as cylinder, right, is at rest, can I say summation of all y forces will be 0? Why? Because the net acceleration along the y direction is 0. It means force on the B side minus force on the A side, that will be equivalent to what? Weight. Right? Pressure on the B side minus A side, that will be equivalent to its weight. Right? Because the summation of all it is equivalent to 0. So can I say pressure at B into area minus pressure at A into area? Can I replace this stuff as density into volume into G? So PB minus PA into area, that is equal to density into G into area into H. Can I say volume of the cylinder, that is area into height? Area will get cancelled, right? Yes, there exists a pressure difference between the 2 point, right, of the cylinder, the two edges of the cylinder, and that is equivalent to rho GH. That is equivalent to rho GH. Suppose this is a surface, the water surface. If a particle is kept at the point A, which is at the height h, below the surface level. So whether we are having any kind of the pressure difference between these 2 points A and B, yes, we are having the pressure difference. At A, the atmospheric pressure is acting, while at B, so the pressure between these two, the pressure difference between these two that will be equivalent to rho GH. Pressure difference between these two will be equivalent. Right? So suppose if it is touching the surface level, then atmospheric pressure is acting. Suppose if it is considered as a particle, then the pressure difference between the surface level, right, and at the position, at the depth, the particle is kept is equivalent to rho GH. Just consider one point, the pressure difference is always equivalent to rho GH. Right. So this is how we are, right, measuring the pressure difference. Right. So can we say the pressure at B, that is equal to PA plus rho of GH. What are the applications of the Pascal's law? We have seen that part. First, hydraulic brakes, sprinklers, water sprinklers, right? Hydraulic lifts. This is the best example of the hydraulic lifts, right? Suppose this side area is A1, right? The force applied is F1. This side area is A2 and force applied is F2. Right? Now, according to the Pascal's law, the pressure is distributed. See, suppose from this side of piston is pressed. Suppose from the left side, the piston is pressed by force F1. Right? Then the same amount of the pressure is going to transmit it equally into the opposite direction, into the all directions. So in that case, right, F1 by A1, that will be equivalent to F2 by A2. In another sense, right, P1 is equivalent to P2. This is the case of the hydraulic lifts. Right? Hydraulic jacks. The hydraulic system that is used inside your bed. Like when you are lifting up some part of the bed to keep the things inside. Right? Okay, there is always a storage given, right? Okay, beneath that part, right? There is always a storage, right? To open that, we are used to lift that, right? We used to lift that. So behind that, okay, there is a mechanism, right, which is known as hydraulics. Okay, if hydraulics is not there, then it is difficult to lift that part of the bed. And if it is present, then we can easily just do like this way. Just apply the minimum force and get the maximum output. Right. So these are some of the applications of the Pascal's law. Right. Now, what does the hydrostatic paradox states? What does the hydrostatic paradox states? See, hydrostatic paradox, see, we saw with respect to the surface level, we are always having the pressure difference at the depth. But what about the one surface level? With respect to one level, there are some pressure variation with respect to depth also and with respect to height also. Suppose if I'm talking about the ocean level, the sea level, right? Then if you're moving on to the depth, pressure increasing. If you're moving above the sea level, pressure decreases. Very simple step. But what about one specific level, right? To understand the pressure difference at one specific level, the concept of hydrostatic paradox is must. Concept of hydrostatic paradox is must. What it states? Irrespective of size or shape of any capillary tube, irrespective of any shape and size of a capillary tube, if water level is same, then at the bottom pressure, right, transmitted by the fluid at the bottom will be equal. Like this way. The level into the all capillary tube is the same, right? Can I say in all of the capillary tube the level is filled with the height h. In all capillary tubes the level is filled with the height, right, h. If this is happening, right, then pressure at the bottom of all tubes will be same. Suppose if I'm talking about point A, B, C, D, E, the pressure difference between A and the bottom, rho GH, B and the bottom, rho GH, C and the bottom, rho GH, D and the bottom, rho GH, E and the bottom, rho GH. That's what actually the hydrostatic paradox is all about. In another sense, if you want to understand this into the more simplified form, at one level, the pressure is always same. Right? At one level, the pressure is always same. Let us take an example. If I'm talking about this level, here also pressure is P, 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 P, because it has a one same level. If I'm talking about this level, here the pressure will be P dash, here the pressure will be P dash, and here the pressure will be P dash, here the pressure will be P dash, here the pressure will be P dash. If I'm talking about the bottom level, PB, bottom level, bottom level, bottom level, bottom level, right, bottom level, irrespective of any size or shape and anything. This is the concept of the hydrostatic paradox. Two simple thing, right? In summarized form, only one simple thing. At one level, pressure is going to same. Below that level, pressure is going to increase. Above that level, pressure is going to decrease. And atmospheric pressure always acts perpendicular to the surface. The most important note I'm going to show you all, I'm going to write in front, right? The atmospheric pressure always acts if the surface is tilted at theta, right? The atmospheric pressure will be tilted at theta. It's not a big deal, right? But it always acts perpendicular to the surface, right? So this is all about the Pascal's laws. Now let's see, right? Okay, how these things, right, what we understood right now are going to help us, right, in solving the PYQs. NEET 2017, awesome sum is asked. Really nice sum, and it is, see, the sum, how it appears horrible in front of you all, na? It is not actually, right? It is quite easy if you really understand the concepts, right? And if you are not stuck into the maze of this grammatical formations, right, then the question is quite easy. A U-tube with the both ends open to the atmosphere is partially filled in the water, which is with the water. Oil which is immiscible with the water is poured on the one side. Oil is poured onto the one side until it stands at the distance of 10 mm. The water rises by 65 mm from the original level. See, this was the initial water level, right? Initially was like this way, both on the same side. With respect to this, it was 65 mm above. Now when the oil was poured from the left arm of an U-tube, right, the water rises by 65 mm on the opposite side. We need to calculate the density of the oil. Very simple concept of hydrostatic paradox and one of the applications of Pascal's law. Concept of hydrostatic paradox, it states that what? At one surface level, pressure is same. At one level, right, pressure is same. It means, can we say that pressure at B, that will be equivalent to pressure at C? Pressure at B, that is equivalent to pressure at C. At B, only oil is present, and it is also up to the height of 65 mm, 65 mm, 130 mm plus 10, 140 mm. So on the left side, can I say, see, both ends of the tubes are open. If the both ends of the tube are open, it means atmospheric pressure is acting. If not, then atmospheric pressure is zero. If it is closed, atmospheric pressure is zero. So here on the B, can I write it is atmospheric pressure plus density of oil into G into the height, that is 140 mm. What will be the pressure at the point C? Now here we are having the water on this side and it is filled up to the height of 65 plus 65, 130 mm. So on the right side, can I say density of the water, right, into G into height of 130 mm, right, plus P atmosphere, because that side is also open. This is gonna cancel. So the density of the oil we are going to have 130, right, into density of water whole divided by 140, right. So finally replacing this value, we are going to get density of oil as 928 kg per meter cube. The C is the perfect answer for this specific question. Two most important things. The first one, hydrostatic paradox, one pressure. At one level, pressure is same irrespective of any shape and size of the capillary tube. And second, the variations of the pressure with respect to depth, it is given as delta P is equal to rho G H. We compared the pressure at B and C, right? At point B, oil is applying the pressure, and at C, the water is applying the pressure. We replaced all of those respective equation and evaluated that stuff. Okay, this is the question of Archimedes principle, and we are going to see afterwards. Now see this. The area of cross section of the wider tube shown into the figure is 800 centimeters square. If the mass of the 12 kg is placed on the massless piston, the difference in the height of the water level is what? When 12 kg was not kept, water level was this. Now when 12 kg is kept, new water level is this. New water level, old water level. The difference is of height h. So it means that whatever, right, the force, that is 12G, it is applied on this cross section area. According to the Pascal's law, force applied from this side, it is going to equally distribute into the all part. Right? It is going to equally distribute it into the all part. Right? So can I say the pressure on the either sides are equal? Right? This is all we have seen into the theory, that is P1 that is equal to P2, that is F1 by A1 that is equal to F2 by A2. Right? Pressure on the either side are equal. Right? Okay, now. So can we say the difference of the water level, right? So what is the pressure difference? Rho GH. Right? Pressure difference is rho GH. Can I say it is 12 into G by area? That is 800 centimeter square into 10 to the power minus 4. Can we cancel out G? Rho into H, that is equal to 12 whole divided by 8 into 10 to the power minus 2. Right? So can I say H, that is equal to 12 whole divided by 8 into 10 to the power minus 2 into density of an object. Right? Okay. Now H, that is equal to 12 whole divided by 8 into we can say 10 to the power 2, right, into density, that is 1000. Right? So H, that will be is equal to 1200, right, whole divided by 8000. 1200 whole divided by 8000. So this is gonna cancel, right? 2 6s are, 2 40s are, 2 3s are, 2 20s are. H is equivalent to 3 by 20 approximately. So this will be equivalent to 15 centimeter. Approx it will be equivalent to 15 centimeter. Right? Approximately it will be equivalent to, right, okay, nearly 15 centimeter, right? Approximately it will be equivalent to what? 15 centimeter. Now let's move on to the next sum, right, of the Pascal's law, right? Okay, see. Okay. A small piston of a hydraulic lift has an area. Area of the piston, right, it is given as 0.20 meters square. Area weighing the force acting on the piston, right, that is equivalent to 1.2 into 10 to the power 4 Newton. Right. The large piston has an area. Area of the large piston, that is equal to 0.90 meters square. The force must be applied to the small piston to support the car will be what? The small piston, a car weighing, okay. Force on small, area of small, force on larger, right, area on the larger, according to the Pascal's law. Smaller has the area of 0.20. We need to calculate the force on the small. Force on the larger is 1.20 into 10 to the power 4 whole divided by area of larger is 0.90. Right? Okay. So force on the small, that will be equivalent to 1.2 into 10 to the power 4 into 0.20 by 0.90. So it's 1.2 into 1.2, right, into 2 whole divided by 9 into 10 to the power 4. Right. So this small, that will be equivalent to approximately 2.7 into 10 to the power 3 Newton. This much amount of the force is applied to the small piston to support the car. A very simple application of the Pascal's law. What is the pressure on the swimmer at 10 meters below the surface of the lake? Pressure difference rho g h. Density of the water, that is 1000. G value is 10. It's 10 meter. Right? So it's 1, 2, 3, 4, 5. It's 10 to the power 5. Right? What is the pressure on the swimmer? Right? Okay. So this is a pressure difference. But the pressure on the swimmer, that is equal to P atmospheric pressure plus 10 to the power 5. This will be nearly equivalent to 2 atmosphere or 2 into 10 to the power 5. Right? Newton per meter square. Right? 2 atmosphere is a perfect answer. Right? This will be nearly equivalent to the 2 atmosphere. So this is all about the Pascal's law. Right? Now, let's move on to the next. Students, we have seen right, the concept of the static containers according to the Pascal's law. There are some examples in which, right, accelerated containers are also there. The concepts of accelerated containers. Right, accelerated container. Suppose let us take an example. This is a container, right? If it is a static, right, then liquid is like this way. Suppose it is getting accelerated in this direction. This is the case of the static container. So it's like this way. Suppose if it is getting accelerated into the horizontal direction, then what will happen? Right? Then as because of pseudo force, right, as because of the pseudo effect, water will push into the backward direction. Right? So the new surface will be like this way. Right? New surface will be like this way. Right? So this will be the horizontal acceleration given to the containers. Right? The horizontal acceleration given to the containers. Right? It will act like this way. So in this case, suppose the surface is making some angle theta with respect to, right? So if I'm applying the pseudo effect, then this will be the acceleration of the frame, right? This is the G, right? Okay. And this one is the theta, right? This one is the theta. So in that case, if I want to remind it all, then we are having tan theta, that is equal to A by G, and A is equal to G of tan theta. This is the formula you all are aware of. Right? This is the formula of the accelerated containers you all are aware of. Apart from this, right, we are having the another case of the vertical acceleration also, and lots of things are there. Right? Apart from this, we are having, right? So this is the horizontal acceleration of the containers, right? So suppose, if you want to move that with what acceleration, what will be the effective acceleration? This is a theta, and this will also be the theta. G effective, right? That will be under root of, right? This one, that is a square plus g square, right? And if you want to know, right, this will be the situation when it is horizontally accelerated, and if you need to calculate the rate, this will be the h1, then pressure at the point P, that will be equivalent to P atmosphere plus rho g of h1, and this h1 can be evaluated using the direct formula, right? With the acceleration of the container, we are having the rotations of the container and torque, but those are direct formulas only, right? And even they hold the less weightage, but it's okay, right? I showed you all with the one simple example so that the student might not get might not have a negative thought into the mind that Indrajeet sir, let's skip that part. Okay, so this was the accelerated container. Now let's move on to the next part of this topic. Thank you. So students, let's move on to the concepts of the Archimedes principle. In this session, we have moved on, right? We have seen the concepts of Pascal's law and its respective application with some of the PYQs related to it. Now, let's move on to the Archimedes principle, the most important part in fluids. What does the Archimedes principle states? It's a very simple thing, right? A very simple thing. Okay, the amount of weight, right, that is immersed inside the fluid, that is equal to, right, the fluid getting displaced. Okay, it's a very simple thing. Okay, I will explain these things into the detail, but first of all, let's move on to the specific visualization, right? The weight that is immersed inside the liquid or a fluid. Suppose, let us take an example. If m kg is there, it is immersed inside the liquid. The same amount of the fluid gets displaced, and here, right, comes the concept of buoyant force. What actual the buoyant force is, right? What actual the buoyant force is. Let us take an example. Suppose this is the water level, the surface level, right? Okay. Whenever any object is immersed inside the fluid, now, or let us take an example if I'm talking about the water. Whenever the object is immersed inside the water, there exists a force that fluid always applies to the object. Always. That force, it is known as buoyant force, right? That force, it is known as buoyant force, right? And the property of applying this force, it is known as buoyancy, right? Buoyant force, students, please, right? I'm again highlighting this term because it is quite helpful, right? And it is important also. The reason is buoyant force is only responsible, right, for the particles, right, those who are floating at a specific depth. Buoyant force is only responsible for an objects, those who are moving on the surface of the water, like steamers and ships. Buoyant force is only the responsible, right, for a particle who is getting sinking inside, right? Indirectly, maybe, right? So this is in the most important terms into the fluid while dealing with the Archimedes principle, right? And some of the concepts of the Stokes laws and viscosity, right? So buoyant force, just keep one thing into your mind. The force, right, applied by a fluid towards an object, okay, there is always a resistance, right? See, it's a very simple example. Suppose, right, without any invitation, if I'm moving on, if I'm entering any, right, X person's house, right, then it will be considered as a trespassing, right? and that trespassing is a legal, what we can say, it's a mistake, right? Okay, it will be a legal action against you all, right? Similarly, if I am entering without permission in anyone's premises, right, it is considered as a trespassing, the legal crime. The same, if I'm entering the premises of the water, then obviously, right, the water, the fluid, right, is going to provide some kind of the resistance against this trespassing of an object, right, which is getting immersed inside it. That property, it is known as, that force, that resistance water is applying towards an object, it is known as buoyant force. Now, what does an Archimedes principle state? It states that, right, an object immersed inside the fluid, an object that is immersed inside the fluid, that is equivalent to, right, the amount of the water displaced, right, amount of water displaced. The weight of an object immersed inside the water, that is equivalent to amount of the water displaced. Second most important terms, buoyant force acts, right, only when the water is getting displaced. Without that, we are not able to identify, right, whether it is acting or not, how much amount it is acting, and lots of things are there, right? So this is a simple case of the Archimedes principle, right? And with this, right, we are having the law of flotation, a very simple thing. Suppose, let us take again an example. It is shown into the visualization. This law of flotation, right, and Archimedes principle, these two things are right, quite important for the underwater vehicles like submarine and all of that things, right? Okay, this law and the Archimedes principle is behind it, right? So it plays a quite a prominent role. Okay, now see, suppose again, if I'm talking about, this is a water level, right, this is a water surface, right? Now suppose what does the law of flotation states? Three examples I want to take. The object that is floating near the surface, the object that is floating at the height h, right, and the object that is at depth. Basically, if I'm talking about for this specific object, two kind of forces are always acting, right? Two kind of forces are always acting. First of all, it's weight. Weight is acting into the downward direction. This weight is acting into the downward direction, and this weight is acting into the downward direction. There is another force which is known as buoyant force, right? That is always provided. It is a kind of a resistance that is provided by the fluids towards an object, right? So yeah, if I'm talking about this object, obviously, right, the buoyant force is acting into the upward direction. If I'm talking about this object, obviously the buoyant force is acting in the upward direction. If I'm talking about this object, right, then buoyant force is acting into the upward direction. Then students, what is the difference between these three cases? All are equal, na? This is also floating at the right at the surface, and it is at the rest. This is at some depth h, but obviously it is on the equilibrium, it is at the rest. It is also, this third object is also synced, right? Okay, and while touching the seabed, this is also at the rest. And what is the difference between these two? These three, in these three cases. So in first case, the weight of the object, it is quite greater than the buoyant force. Here, the buoyant force is quite negligible. So because of that, I'm extremely sorry. Just hold on, right? Just hold on. Okay. Not this. See, here, I'm extremely sorry. Here, the weight of the object is quite less than buoyant force. Buoyant force is of the maximum value. weight is quite less than buoyant force, right? That's why the particle is floating on the surface. So in this case, can I say it is, right, floating, right, on surface? It is floating on the surface. In second case, suppose if it is floating at some depth h, so at that time the weight is balanced by the buoyant force, right? On this principle submarine works, right? On this principle submarine works. If weight is balanced by the buoyant force, right, then all upward and downward forces are going to balance. It means summation of all y forces will be 0, and according to the conditions of the equilibrium, the net acceleration along the y will be 0. If this second condition is satisfied, then object can float at specific depth inside the or beneath the water level, right? Beneath the water level. Now what about the third case? This was the first case, this is a second case, this is a third case. Now weight exceed more than buoyant force, right? Buoyant force is acting, but it is quite negligible as compared to this weight. So in this case the object sinks, right? So this is having the deep relation with the Archimedes principle, right? If you are immersing an object inside the fluid, right? Okay, after, like, suppose, let us take an example. If I'm having a sphere in my hand, suppose it is, right, immersed, it is getting immersed inside the liquid, right? It is getting immersed inside the liquid. Then what will happen? We will be having the three possibilities. See, if it is getting immersed inside a liquid, it is for sure, according to the Archimedes principle, the same amount of the water will get displaced. But again, we are having the three possibilities: whether it will float on the, above the surface level, right, or it will be like float it, or it will be remain in equilibrium at some depth h, or it will get sinked. So these are the three possibilities, and that is known as law of flotation, right? That's the law of flotation. So guys, remember this thing, right? This and Archimedes principle, these two things are, right, we are going to use a lot, right? We are really going to use a lot in this. Now there are some cases, right? Okay, we will understand these cases of the Archimedes principle with the some of the examples. Okay, so let's move on to the first part. First, suppose I'm talking about the cube, right? I'm showing you all an example of a cube, right? A cube that is having length L, right? So the volume of the cube, can I say, right? I'm talking about the cube. So volume of the cube, that is area into length, right? Area into length. The first case, right? How to apply? See, this all are the cases, right, we are seeing, in which I will explain you all and how to apply this principle to get the correct answers, right? Suppose in this question it is mentioned that the object, that it is of mass m, right? Density of the object is rho 0. It is immersed inside the fluid. The length of the object is L. The x part of the length is getting immersed and the object floats, right, among the entire cube, right? The situation is like this way, right? I'm showing you all a cube, right? This is a cube. Let us take an example, right? The x part of the cube is getting floated. You can see, you can understand this stuff. The x part, this length of the cube is getting floated. Right? Now in this case, how we are going to find the value of x? In this question it is mentioned. See, density of the fluid is rho. Let us take an example, it is rho L. Now how we are going to? First step, system is in equilibrium. Summation of all y forces are 0 as system, right, is at rest. Summation of all y forces is 0. It means the system is at rest, right? So very simple thing. It is at the rest now. It means its weight is balanced by the buoyant force. Its weight, it is balanced by the buoyant force. What does the weight states? It's m into g, What does the buoyant force states? That is density of the fluid into volume immersed inside the fluid. Now, here's the point where students always used to commit a mistake. Always. They used to apply the buoyant force on the entire object. No. Buoyant force only act to that much part of an object that is immersed inside the fluid. Here you can see the entire part is not immersed inside the fluid. Only the X part is immersed. So it means that buoyant force is only acting to this much part. Right? The L total is L. The L minus X part is outside the L. Right? So it means that it is mg and that is equal to density of the liquid, right, into C. I have written into the formula volume immersed, right, into G. Can I replace this m as density of the object into volume of the entire object? So this is always considered in air. This is always considered in air. This is what about the fluid is, and we need to compare this too, right? Density of the liquid, volume immersed into G. So this G is going to cancel. Density of object, volume of entire object, density of liquid, volume immersed. So it is density of object. If I'm talking about the entire object in air, can I say it is area into length? Now, density of liquid, right? Area will remain same, but what part of L that is immersed inside the water? X. So here what we are getting, area will get cancelled. So density of object by density of liquid, that is equal to, right, into L, that will be equivalent to the value of X. This is how, using the law of flotation and Archimedes principle, right, this X is calculated. Second case, suppose, right, this is liquid 1, right, and this is liquid 2. If I'm taking two liquids, right, this is the second case, right, I'm showing you all how to apply this, right, okay. Suppose this is a liquid 1 and this is a liquid 2, right. Suppose object is inside the fluid by X. Object is inside the fluid by Y. In first case it is X, in second case it is Y, right? In first case it is X, in second case, right, it is Y. Then how we are going to calculate? This kind of questions are there. How we are going to calculate the ratios of this densities of the two fluids? In both of the cases, right, if object is immersed inside the water, it means the same amount of the water has been displaced. If the same amount of the water has been displaced, it means the buoyant force is acting. And if there is a presence of buoyant force and object is stationary, it means according to the law of flotation, weight is getting balanced. So here in this case, weight that will be equivalent to mg. Here in this case, weight will be equivalent to mg, and that will be equivalent to buoyant force. So here, can we write density of the object into volume into length? It is density of the fluid 2, right, into, sorry, not volume. This will be area. And this will be area into X, right? So here density of the object into L is equal to delta 2 into, this is Y, I'm sorry, Y. Can I consider this as equation number 1? Yes. Here, density of the object into area into L, that is density of the fluid 1, right, into area into X. Again area is going to cancel, density of L into density of 1 into X. Can I consider this as equation number 2? Comparing 1 and 2, right, I'm getting rho 1 by rho 2, that is equal to X by Y. This is how we are using the Archimedes principle. These are the two most important cases. Now let's move on to the third case. Suppose there is only one container. Only one container is there. The same container. In the previous case, what we saw, see, first of all, we saw the case of only one single fluid, a single fluid. After that, we moved on to the comparison between the two fluids, right? The comparison of the buoyant force between, right? Comparison between the two fluids, right? Right. Now we are moving forward to the third case in which there is only one. Right? There is a presence of only one container in which two fluids are present. This is a fluid of density 1. This is fluid of density 2. Object is immersed inside the fluid, right? X part is there like here and Y part is like this way. Sometimes instead of X and Y, volume is also given. So it is a kind of an alternate thing, right? Okay, you should be aware of. If we need to deal with the volume, then answers will be quite easy. Evaluation part would also be right, less confusing, right? And suppose if you need to deal with this distances, okay, it happens. We are doing that stuff. So in this case, what will happen? Two fluids are there. Okay, density of an object inside the air. If I'm talking about an air, right? If I am talking about an air, then what will happen? The density of the object is rho, right? And length is L. Object is in between two fluids. This is fluid 1 and this is fluid 2. Object is in between two fluids, right? So in this case, right, fluid 2 is also applying the buoyant force, right? Fluid 1 is also applying the buoyant force. Buoyant force is applied, right, by both of them towards an object. It means that according to the law of flotation, we were balancing this stuff, right? So this will be as because of fluid 1 and 2 both. So weight in the air is mg. This will be the buoyant force, right? Okay, this will be volume of 1 into g plus rho 2 volume of 2 into g. Suppose if I'm replacing this thing, that density of the object into area into length, that is density of 1 into area into x plus density of 2 into area into y. This area is going to cancel, right? So density of object into L, that is density of 1 into x plus density of 2 into y. Okay, this is how Archimedes principle is applied, and this is a third case. Fourth case, suppose you have seen a float. Inner radius is R, outer radius is capital R. You've seen the float, that tube, whenever you used to move on to the water park or something, right? Then you're using this float, right, to enjoy the waves, right? What happened when this float is completely immersed inside the water? Another case, float is completely immersed. Again, obviously, if it is in equilibrium, then it's a very simple thing. The weight will be balanced by buoyant force. Now, this is entirely inside the object. So this is inside the fluid. So this will be the part of air. Density of the object into volume of an object into G, it's okay. Density of the liquid, that is volume inside the liquid. Now there is a difference. If it is in air, right, if it is in air, then this much amount of the mass will not be considered. This much part is hollow, it is vacant. Tube is a kind of a 3D structure, right? But this much part is vacant, right? So whenever this tube is kept into the air, right, this place will not hold the mass. But when this float is entirely immersed inside the fluid, the water is getting displaced from this hollow space. So it means it will hold the mass inside the fluid. In the air, this space is vacant. It is not going to hold a mass. So while considering, right, if we are considering this part in air, so this thing will be subtracted. But when the same float is immersed inside the water, okay, or the fluid is getting displaced through it. On immersing inside the water, the fluid is getting displaced through it. So it means, yes, the buoyant force is acting and it will hold the mass. Four by 3 pi capital R cube minus small r cube, density of the fluid 4 by 3 pi capital R cube. This thing is going to cancel, right? So finally we are having the density of the object by density of the fluid, that is equal to r cube by r cube minus small r cube, right? This is how Archimedes principle is applied in, right? Law of flotation is used. Okay, so these are some of the cases, right, of the Archimedes principle, right, and the law of flotation. Now let's move on to the, right, some of the important examples related to it. And apart from this thing, right, we are going to see this. It's okay. Now there is a concept of an apparent weight. Now what does this apparent weight means? Okay, so let's move on to this question, right? A crown made of a gold and copper. Okay, this question is quite different, right? As we discussed, we saw all of those cases, right? Okay, this question is a bit different. In all of those cases, I always used to say that according to the law of flotation, the weight is always balanced by the buoyant force. But here, in that case, loss was not considered. And generally, this kind of sums are asked on basis of loss of weight. Loss of weight means what? It is weighting x in air, but less than x inside the fluid. Let's see this question to understand that stuff. A crown made of gold and copper weighs 200 gram in air and 198 gram in water. There is one crown. It is made up of gold and copper both, right? Weight in air, that is equivalent to 110 gram, and weight in water, right, that is 12 gram. Here is a loss of 12 grams. If I'm talking about then, right, loss, then it is equivalent to 12 gram, right? As if we are comparing the data of air and water, then we are having the loss of 12 gram. When it is immersed inside the fluid, right, the 12 gram of the object is getting lost. Now what we need to calculate? We need to calculate what is an actual weight of a gold inside the crown. Very simple thing. Weight is balanced by the buoyant force. But here we are having the two kind of the objects. So density of the gold into volume of gold plus density of in copper into volume of the copper, that is equivalent to 210 gram. Right? G will get cancelled. So can I say this is okay, density of the gold is 9. This is 19.3. It's 19.3 into Vg plus 8.5 into Vc, that is equivalent to 210 gram. Can I consider this as equation number 1? Yes. But this is all about what actual thing is going on in air. What about when it is immersed inside the fluid? There is a loss of 12 gram. So whenever it is immersed inside the liquid, right, density of the liquid, volume of gold, density of the liquid, volume of copper, that is equivalent to 12 gram. So it means that density of the liquid into Vg plus Vc, that will be equivalent to 12 gram. Can I consider in gram, right, density as 1? So what will be Vg plus Vc? Vg plus Vc, that will be equivalent to 12. Can I consider this as equation number 2? Solving 1 and 2, what we get? Solving 1 and 2, right? Okay. can I multiply this as, okay, 19.3 Vg plus 8.5 Vc, that is equal to 210, right? And if I'm multiplying 19.3 Vg plus 19.3 Vc, that will be equivalent to 19.3 into 12. Solving this, right, we are getting Vg as 10 and Vc as 2. If I'm multiplying with its weight, right, I'm getting approximately, sorry, if I'm multiplying with its density, approximately I'm getting, right, the mass as density into volume, that is 10 into 19.3, right, it is equivalent to density into volume, and that is 193 gram. So this is another case, right, okay, in which we are using the Archimedes. See, same na, right? Okay, air and fluid we are compared, right? We've used the concepts of the, right, Archimedes principle and the law of flotation, right? Same thing, but there is only one exception. What here? Loss needs to be considered, right? So like this, we are having the another example, right? So this I'm giving you all in the homework. You can answer this stuff. You can answer this question beneath the video, right? Beneath the video. Okay, now see, the density of the steel is 9,000 kg per meter cube. Density of steel, that is 9,000 kg per meter cube. And the density of the water is 1,000. If a cube of a steel, that is 0.100 meter, on each side is placed in a tank of water and weighed while under the water, then what will be its apparent weight? Right? What will be its apparent weight? Right? What is the length of the cube? Length of the cube, that is 0.00. I'm sorry, length of the cube is 0.1 meter. Length of the cube is 0.1 meter. Then what is the volume of the cube into the air? That is 0.1 into 0.1 into 0.1, 10 to the power minus 3 meter cube. This is the volume of the cube into the air. Now we need to calculate the apparent weight of this cube, right? Now what is an formula of the apparent weight of the cube, right? What actual is the formula of the apparent weight of the cube? So what will be the formula of apparent weight of an object? See, the apparent weight of an object, that is equal to its actual weight, right, minus buoyant force. If I am considering the actual weight, can I say it is density of the object into the volume of the object into g, minus density of the liquid into velocity, volume of an object immersed inside the liquid into g, right? So here Vg are constant, so apparent will be, right, okay, apparent weight, yes. So this will be density of an object, right? It's approximately 8,000, right, into V0 into g, right? So this apparent weight would be 8,000 into 10 to the power minus 3 into g, right? So this will be get cancelled. It will be equivalent to 80. Nearly equivalent to 80 if you are considering, right, g value as 10, right? If we are considering g as 9.8, then it will be approximately equivalent to 78.8 Newton, right? Approximately equivalent to 78.8 Newton. So this is a new concept of the apparent weight that is also used into the, right, this laws, the Archimedes principle and the law of flotation. A hollow metal cube, another question, a hollow metal cube of 1 meter, length of the cube is 1 meter and it is a mass of 600 kg. How deep it will sink when placed in the weight of the water? How deep it will sink? It means they are asking about the position where W will be equivalent to FB. How deep it will sink, it doesn't mean we are going to find out the depth of the ocean. No. When it will start sinking, right, the things will be not in our control. Okay. the calculations are in our control up to what moment, up to the moment where weight is balanced by the buoyant force, right? So in this case, can I say this weight, right, that is equivalent to buoyant force, right, or this mg, right, that is pressure into area, right? Force, can I replace this force as pressure into this specific area, right? So now okay, this mg will be 600 into 10, right, and that will be rho g h into area, right? Okay, now this will be, this is going to be the same, so this will be 6000 and this will be rho will be 1000 into 10 into h. So here h, maximum it can sink up to the 0.6 meter. Maximum it can sink up to the 0.6 meter, right? Suppose this is a water level, okay, at the depth of 0.6 meter, the weight is balanced by its buoyant force. Beyond this, object will get sink, right? So this is what all the Archimedes principle and everything is all about, okay? So now let's move on, right, to the equation of continuity and the Bernoulli's principle, the most important stuff. Now what does this equation of continuity states? You all are aware of the four fundamental, right, these principles, the four fundamental laws of conservation, laws of conservation of energy, laws of conservation of charge, laws of conservation of linear momentum, and conservation of angular momentum. Right, you all are completely aware of this thing. But here, to understand, right, the concept of equation of continuity, we are going to move on, right, to conservation of mass. Now what does this conservation of mass states? And before moving on to the concept of this conservation of mass, right, first of all, I want to tell you all are completely aware of how many types of fluids are there, how many types of, not fluids, how many types of flows are there. The one that is the streamline flow, the turbulent flow, right? So this kind of things you all are completely aware of. Even you all are aware of these values of the Reynolds number, right? In between 2000 and 3000, greater than 3000, it is a turbulent flow, right? These things you all are aware of. But don't get worried, the concept of the streamline and turbulent flow, again we are going to see into the Bernoulli's equation, okay? But here, what actual the conservation of mass is, let us understand this visualization. Suppose this is a part 1, right, and this is part 2. In between part 1 and in between part 2, something is common. In between part 1 and part 2, something is common. What it is? Mass entering the pipe, that is equivalent to same, it is equivalent to mass leaving the pipe. Mass entering the pipe is nearly equivalent to the amount of mass leaving. That's the conservation of mass. Now if this amount of the mass that is entering is equivalent to leaving, then how we are going to identify the right variations, right? Okay, we are seeing this variation. Now let us take a very simple example. If the area of this much part is A1 and if area of the smaller part, right, it is A2, there is a difference into the areas of the cross section, na? Right? If there is a difference into the area of cross section, then obviously the rate of the flow of the fluid, right, will get affected. Here the velocity of the fluid will be something else, here the velocity of the fluid will be something else, right? Here the velocity of the fluid will be something else and here it will be something else. Then and see, if you want to conserve this mass, right, then there should be some relation between, right, area and velocity. there should be some relation between area and velocity. Then and then it should be, then and then it is possible, right, that the amount of the mass that is entering from the one side of the pipe, the same amount of the mass it is leaving on the another side. So using this relation, kindly consider as no loss. So now you all are aware of what actually the conservation of mass is. Now let's move on, right? Okay, we are now aware that we need to find, right, if we need to conserve the mass, then we need to find the relation between area and velocity, and it is for sure also. Why? I'm giving you the example of the day-to-day life. I'm giving you all the example of the day-to-day life, right? See, whenever we are having a pipe into a hand, and if we are covering the half part of the pipe with your thumb, okay, then the velocity of the fluid suddenly get increased, right? If you are removing the thumb, again the velocity will get decreased. So if you are decreasing the area, the velocity is getting increased, and if you are increasing the area, the velocity is getting decreased. So there is some relation between area and velocity, and that is all about, that is what this continuity, the equation of continuity, is all about. Mass is conserved. It means mass that is entering equal to mass leaving. Mass that is entering, that is equivalent to mass leaving. Density into volume. Density into volume. Suppose this part is having the area A1, this part is having the area A2. At this part velocity is V1, and then this part velocity is V2. So can I say density, volume can I consider as area of the cross section into length L1, area of the cross section, right, into L2. Dividing the times on the either side, right, dividing the times on the either side, right, here it will be area, right, okay, hello, I think as because of this visualization, right, this thing is going on, right, okay, so here it will be area A2, okay, so here, okay, so it's ρ1 A1 V1, that is equivalent to ρ2 A2 V2. This is the actual equation of continuity. This is an actual equation of continuity. The actual equation of continuity. But in this case, right, suppose the density, right, at the entrance point of the pipe is equivalent to, right, the density at the leaving, while it is leaving, right, then we can say, suppose if ρ1 that is equivalent to ρ2, then and then we can say A1 V1 that is equivalent to A2 V2, and AV is equal to constant and A is inversely proportional to V. Generally, if you've seen many sessions, then they used to consider AV is equal to constant, A is inversely proportional to V, this as the equation of continuity, but wrong. Actual equation of continuity is this: if ρ1 is equivalent to ρ2, then and then we can say that yes, A is inversely proportional to V, else we need to consider this density. Let's have an example to understand this. Right, let's have an example to understand this. Suppose we are having this kind of the configuration, and this is a very famous question, right? Okay, this is a very famous question, okay, that you all are aware of, okay. Suppose this is a cross section area of A, right? This is a cross section area of A by 2, and this is A by 2. Here the rate of the velocity of the fluid, it is given as 10 centimeter per second. Here we are having 2 centimeter per second, right? At that point we are having 2 centimeter per second, right? Okay, let's change this stuff, right? I'm sorry, again I'm writing this question. Suppose this area of cross section is A, the velocity of the fluid is 10 centimeter per second. Here the area is A by 2, right? The velocity, consider it as a 3 centimeter per second. Here suppose it is A by 4. What will be the rate of the, what will be the right speed of the fluid? Again we are using the equation of the continuity. This will be the entrance point and this two are the leaving. So can I consider AV, that is equal to A1 V1 plus A2 V2. Now see, density, right, while when the fluid enters the pipe, the density is rho, and it is the same, it is equal while it is leaving, right? So in that case I can consider the rho will get cancelled. I'm using the direct equation as AV. So AV, that will be equivalent to A1 V1 plus A2 V2. A into 10, that is equal to V1, that is 3 into A by 2 plus A by 4 into V. We need to calculate V. This A will get cancelled, right? So 10, that will be equivalent to 3 by 2, right, plus V by 4. Okay, so it's 20 minus 3 by 2, that will be equivalent to V by 4, right? So it's 17 by 2, that is equivalent to V by 4. V is equal to 34 centimeter per second, right? So from this, the velocity of the fluid, we are getting it as a 34 centimeter per second. So this kind of the equations of the continuities are used, right? Even this is also used with the Bernoulli's equation. Okay. Now, let's move on to the some sums related to it. The blood is flowing at the rate of 200 centimeter per second. Now see, directly rate is given. In a capillary of the cross section area 0.5, the velocity of the, see, area of the cross section of the capillary is 0.5 meter per square, right? The rate is already given, right, as 200 centimeter cube per second, right? Okay, then what will be the velocity in mm meter per second? Okay, see, according to the equation of continuity, AV, that will be equivalent to rate. Now rate is 200 centimeter cube per second, but we need answer in mm per second, right? Okay, mm per second. So can I convert this thing into mm? 200 into 10 to the power minus 3 mm cube per second, right? Area will be 0.5. If I need to consider, I'm sorry, this will be plus 3, right? Just hold on, there is a bit of conversation. Okay, first of all, let's calculate this stuff. Okay, don't get worried. Okay, what is an area? 0.5. Okay, let's replace 0.5 into velocity. Rate is 200, so it is 200 into 10 to the power minus 6 meter cube per second, right? So this will be V is equal to 2 into 10 to the power minus 4 whole divided by 0.5, right? So we are getting the value, this is meter per second. Okay, don't get worried, we will convert it into the centimeter per second. This 2 divided by 0.5, that is 4 into 10 to the power minus 4, right, meter per second. If I am converting this into mm, that is 4 into 10 to the power minus 4 into 10 to the power 3 mm per second. So V is equal to 4 into 10 to the power minus 1 mm per second. V is equal to 0.4 of mm per second, right? Using the equation of continuity, we got that answer, right? The flow of the water in the Healy area is an example of this streamline flow. Okay, now you all get confused what actually the streamline flow is. Streamline flow means what? I'm taking 3 points. Suppose this is a pipe. I'm taking the 3 points. point A, point B, point C. Now I am talking about a imaginary fluidic particle. I am talking about imaginary fluidic particle. Imaginary fluidic particle. Suppose it is at this point. First of all, it is crossing through point A, then it is crossing through point B, and then it is crossing through point C. When this flow will be considered at this streamline? Suppose the velocity of the particle while it is entering the pipe, it is P, and when it is at point A, the velocity is fixed, that is A tangent to the path. Suppose the same fluidic particle is crossing through point B, velocity at that point is fixed, tangent to the path. Suppose it is crossing through point C, velocity at that point is fixed, tangent to the path. We are not interested in the amount of the velocity particle is having while entering into the pipe. No. When it is reaching at the point A, velocity will be VA. When it will reach at the point B, velocity will be VB. When it will reach at the point C, velocity will be VC. This kind of the fluid is a streamline. Right. What is a turbulent flow? Harsh flow, flood, turbulent flow, tsunami, turbulent flow. So do you think in the hilly area there is a possibility of a streamline flow? No. False. Flow is always turbulent. Flow is always turbulent into the hilly area. Right. Always turbulent. Right. It is always turbulent into the hilly area. Right. A straight or a curved path such that tangent to at any point gives the direction of the flow of the fluid. Right now we have discussed tangent to any point that shows the direction of the the flow of the fluid. This kind of the flow, it is known as the streamline. Right. This was all about the continuity equation. Now let's move on to the concepts of the Bernoulli's equation. What does it states? See, Bernoulli's equation is nothing else but directly we can compare it to the conservation of energy, and indirectly we can compare this Bernoulli's equation to conservation of momentum if system is considered. But directly we can correlate the Bernoulli's equation to the conservation of energy, and whatever the things are going on naturally, if you want to oppose that, this Bernoulli's equation is used. I'm going to give you all an examples to understand this thing quite easily. Why the Bernoulli's equation is used? Suppose if you are having the glass of water in your hand, and if you're pouring like this way, if you're tilting the glass like this way, then how the water will flow? Obviously from the higher to the lower part. It is a natural thing, as because of the gravity, water always move from the higher to the lower part. If you want to, forcefully, if you want to move a water into the opposite manner, Bernoulli's equation is used. Suppose if I'm talking about a skydiving, if you are moving at some height, and suppose if you are suddenly jumping out of that aircraft, suddenly jumping out, so in that case I want to tell you all, it is a general process, it is a general that you will get constantly accelerated toward the center of the earth with the constant acceleration g. This is a phenomenon that is known as a free fall. Yes, we are considering the air resistance in it. Generally theoretical, from the theory point of view, you are not considering the air resistance, but in this case, let us take an example, we are considering the air resistance. Now what will happen? This is a natural phenomena. Whenever you will be diving from the right height, obviously you are going to come to the land, to the near towards the center of the earth. But if you want to move on to the reverse phenomena, Bernoulli's equation is applied. Taking off of an airplane. The roof of the house, it is placed. Something irregularities are going on. It is moving. The shed is moved away. Shed, right, moves away. This is because at that point we can apply the Bernoulli's equation. It is not for sure that in all the phenomena that we need to move on against the nature and we are applying the Bernoulli. No, these are the one of the examples, right? Okay. See, physics is all about how to understand things easily, right? So for that we need to keep some examples, and I did that, right? It is not for sure that all the times whatever the phenomena that are going on artificially, right, at that point of time you can apply the Bernoulli's equation. No. To understand that stuff, this kind of examples are much needed. So Bernoulli's equation is nothing else but a conservation of energy. There are some noteworthy points related to the Bernoulli's equation. It is always applied with respect to the reference point. It is always applicable to incompressible fluids. In another sense, they are only applicable to streamline flow. Flows, they are streamlined. Right? Flows, right? They are streamlined. There are some, apart from this, lots of things are there, but this thing are quite enough, right, to understand this concept. So suppose I'm talking about, I'm taking an example of a day-to-day life, right, at my home, right, using the submersible pump, using a pump, right. Again, I want to just pump out the water from the ground floor to the topmost part, right, so that tank at the topmost terrace, right, the terrace, it should get filled, right, and then I can get the supply of water at my home. So this is the bottommost part which is at the height h1. This is the topmost part, that is terrace, that is at the height h2. The cross section of the bottommost part is a1. At this position the fluid is moving on with the velocity v1. The topmost part is cross section is a2. At that point, right, the fluid is moving on with the velocity v2. So can I say in between point A and B, can I apply the conservation of energy? Right. So what does it states? Work done by all forces, that is equivalent to change in kinetic plus change, nothing, change in kinetic energy. Work done by conservative, work done by non-conservative, work done by external, that will all change in kinetic energy. We need a reference point, right, with respect to which, right, with respect to the reference point we need to apply the Bernoulli's equation. So this will, the ground, right, it will be our reference point, right, the ground will be our reference point. Whenever the conservative, see, one part of the pipe is at the height h1, one part of the pipe is at the height h2. It means when the fluid is flowing, obviously the gravitational potential energy is going to play the important role. So whatever the work is done by the non-conservative force, it is going to store into the form of the change in the potential energy. So we are getting the final conservation of energy like this way. Non-conservative force, friction, we are not considering, so it means the equation leads to the external force, no friction, no friction in pipe, right? Now who is an external agent, right, doing work to pump out the water from the bottommost part of an house to the terrace. That is pump. Some pump acts like an external agent. Some external agent is doing the work. External agent is doing the work, right? So can I say work done by external agent, that is equal to half m v final square minus v initial square plus, right, can I replace it, mg, that is h2 minus h1, right, h2 minus h1, right? Okay, now so here work is done by the external agent, that is equal to half mass, can I replace it at density into volume, right, into v2 square minus v1 square plus density into volume into g into h2 minus h1. Work is done by external agent, external pump. Can I replace it as PV, that is equal to half rho volume v2 square. This v is of the volume, this v is of the velocity, right, plus rho vg h2 minus h1. V is gonna cancel. P2 minus P1, that is equal to half rho v2 square minus v1 square plus rho g, right, h2 minus h1. Rearranging these terms, I am getting P1 plus rho g h1 plus half rho v1 square is equal to P2 plus rho g h2 plus half rho v2 square. P plus rho g h plus half rho v square is equal to constant. This is the Bernoulli's equation, right? This is the Bernoulli's equation, right? This is the Bernoulli's equation is all about. It can be applied to any 2 points, but with respect to the reference. Now in this, suppose if you want to compare the rate of the flow of the fluid, right, using the, if you want to use the equation of continuity in this, right, we can use this. But indirectly you all should aware of what actually the Bernoulli's equation states. Venturimeter is one of the applications of the Bernoulli's equation. This is used to calculate measure the rate of flow of incompressible fluids. To measure the rate of the flow of the incompressible fluids. Suppose let us take an example, right? This is area of cross section A1. The velocity of the fluid is V1. This is cross section A2. Here it is V2. Now we need to calculate the rate of the velocity of the fluid, right, at this position of the time, at this point of, right, at this point of the pipe, and that fluid is an incompressible fluid. Then we can use this by means of the Bernoulli's equation. Same. How it is applied with respect to the reference point. How it is applied with respect to the reference point. Suppose this is the reference point, ground, with respect to which, right, we are applying the Bernoulli's equation. We needed 2 points, right, about which we need to evaluate this and write down the entire equation. So with respect to this reference point, I'm selecting 2 points. This is a point number 1 and this is point number 2. At point number 1, if I'm writing on this equation, this is open P. Let us take an example. Suppose if it is not open, can I say this as P1 plus half rho, just hold on, V1 square plus rho g h1. I am writing down the Bernoulli's equation, P2 plus half rho V2 square plus rho g h2. Now everything is going at the same surface level, See, the entire pipe is at the same surface level with respect to the reference point. It means this thing we are going to cancel it out. P1 minus P2, right, plus half rho V1 square is equal to half rho V2 square. Evaluating this, we are getting P1 minus P2, right, whole divided by rho plus V1 square is equal to V2 square. Now, we need to calculate the value of V2, but we are having the two unknowns here, V1 and V2 both. So in that case, we need to use the equation of continuity. So according to the continuity equation, right, we can say that A1 V1 that will be equivalent to A2 V2, right? So replacing V1 as A2 V2 whole divided by A1. Replacing this equation here, so we are getting it as 2 P1 minus P2 whole divided by rho plus A2 square by A1 square, right? And that is V2 square is equal to V2 square, right? So finally we are getting the equation of V2 that will be equivalent to what? Under root of, right? If I am rewriting this term, that is 2 P1 minus P2 whole divided by rho, right? That is equal to V2 square will get common, 1 minus A2 square by A1 square, right? Okay. So this will be 2 P1 minus P2 by rho 1 minus, right, A2 square by A1 square. This is the the velocity of the fluid at this point using the Bernoulli's equation, right, by means of the device that is known as venturimeter, which is one of the applications of the Bernoulli's equation, right? So this is how the Bernoulli's equation is applied with respect to the reference point. 2 points we needed. Now the next application, Torsley's law, in which we are going to calculate the velocity of a flux. Same Bernoulli's equation we are going to use with respect to the reference point, and we are going to apply it between 2 points. Suppose I am having tank. The height up to water is filled in the tank is h. Now at the small height h, right, one hole is made, and from which the water is getting right, when water is getting out of it. So at what speed it is moving out, that is known as, or what velocity it is moving out, that is known as velocity of a flux. Using the Bernoulli's equation we are going to calculate this stuff. Using the Bernoulli's equation we are going to calculate this part. What will be the reference point? The ground will be the reference point, right? With respect to the reference point, on which two positions you want to apply the Bernoulli's equation? Number 1, number 2. Write down. Number 1, P1 plus half rho V1 square plus rho G capital H. With respect to the reference frame, reference point, the height is capital H for position 1. Second is P2 plus half rho V2 square plus rho G. Now, if I am talking about the hole with respect to the reference point, then it is height is h minus small h. So here it will be h minus small h. Whatever the distance is there of an object with respect to the reference, we need to consider that only. Upper part of the surface is closed, 0. Well, the fluid is quite slowly, it is like moving quite slowly. So at this position the velocity is also not there. So rho g h, that is, suppose if the the fluid is like moving out of this hole, right, and at that point the atmosphere, the P2 will be P atmosphere rho v square plus rho g h minus rho g small h. So this thing will be get cancelled, right? So rho g of h, that is equal to P atmosphere plus half rho v square, right? Okay, so from this we are going to calculate. Okay, so rho g h minus P atmosphere that is equal to half rho v square, right? So this will help us in calculating the velocity of a flux, right? Okay, this will help us in calculating the velocity of a flux, right? Okay, or suppose if you are considering it as an open container, this is for the closed container. For open container, right, for open container, this P atmosphere will also get cancelled, so it is half rho v square, that is equal to rho g h. So in that case, velocity of the efflux, it will be 2g h. Different cases are there, open case, open container is there, close and everything, lots of things are there, right? Okay, lots of things are there. Okay, but generally it is not important to understand, right, how questions are solved. Instead of that, it is important to understand how Bernoulli's equation is applied. This is what I showed you all in front. Bernoulli's equation, how it is applied, how we can correlate the Bernoulli's equation to conservation of energy, right? Derivation of that, venturi meter, how it is applied, how we can use the continuity equation in this, right? Torsley's law, how it is applied. It is important how it is applied. Rather than to find out any approach or any shortcut, it is important to understand how Bernoulli's equation is applied. The things are going to be quite easy for you all, and even up to the mains level, right? You will solve the sums, right, quite easily up to the mains level. Okay, hope so you'll understand this stuff, right? Now let's move on to the next part. In Karnataka NEET 2013, a fluid is in a streamline across the horizontal part of the variable cross section. For which of the, okay, see, for the variable cross section, we all are aware of the continuity equation. A is inversely proportional to V. Velocity is more, area is less. Suppose, first case, velocity is high, area is less, pressure is equal to force per unit area. Velocity at the maximum at the narrowest part. Narrowest part, it means area is less. Narrowest part, it means area is less. Velocity of the fluid will be more. And the pressure is maximum at the widest part exactly. The first one is going to be the same answer. First one is according to the continuity equation and the definition of pressure. A small hole of the area of cross section 2 mm square is at the bottom of the fully open tank. There is a tank of the height 2 meter, right? The height is of 2 meter. Open tank it is, right? Okay, at the bottom, right, area of the cross section 2 mm square, right, hole is kept. What will be the rate of the flow through the open hole? Okay, it's very simple. According to the Torsley's law, the velocity of efflux, see, as I told you all, into the case of open containers, right, into the case of the open containers, right, see, velocity of efflux is under root of 2gh, right? So the same equation I'm going to use in this, right? So that will be equivalent to under root of 2 into g into h. Height is 2 meter, so it will be 4 into g under root of 4g, so it's 2 under root of g. This is the velocity of efflux, right? What will be the rate of the velocity? The rate of the velocity, that is AV, is equal to rate, so that is 2 under root of 10 into, what will be the area? 2 mm square. It's 2 into 10 to the power minus 6, right? 4, right? So this will be equivalent to 4 under root of 10, okay, into 10 to the power minus 6. Okay, so it's 4 under root of 10. So this is nearly equivalent to, pi square is always equivalent to 10. So pi, that will be under root of 10, nearly. So this will be nearly equivalent to 12.3 into 10 to the power minus 6 meter cube per second. This is the rate B is a perfect answer. In NEET 2019 equation, the question on the Bernoulli's equation, right, and the rate of the flow has been asked. One of the applications of the Bernoulli's equation. Is Bernoulli's principle essentially the conservation of momentum? Actually, it is a conservation of energy, but in some of the cases, indirectly, we can consider it as a conservation of momentum. If system is considered with this conservation of momentum, lots of complications are there. But for now, for the syllabus of 12th JEE, we are considering as a conservation of energy, right? So a hole is there at the bottom of the tank having water. If the total pressure, this is a homework from my side. You have to do by yourself, and you can answer this stuff beneath the video, right? Okay, this is also same. Some of the sums are there. And you will find it into the this thing. You will find it into the notes, right? Whatever getting from the link, right? So you can just do that. Okay, you can just solve off those stuff and you can answer beneath the video. So now some part of the things are remaining, like viscosity, what actually the Stokes law is, and the soap bubble theory and the rise of the liquid into the capillary tube. Okay, so let's move on to this kind of this stuff, right? Thank you. So students, now let's move on to the new concept of viscosity, surface tension, Stokes law, and rise of the liquid into the capillary tube, the remaining part. Okay, so see, viscosity. If we want to understand this stuff, let's take an example of the Dabur ad, right? What it states, viscosity. First of all, in simple terms, if we want to, right, resistance to flow of fluids. A simple definition. Okay, in thousands of the resources, lots of definitions are there, but in the simple terms, if I want to define the viscosity, then, right, resistance to its own flow, it is defined as the viscosity. Let us take a very simple example to understand. Suppose if I am having two jugs in my hand, one is full of water, second is full of honey, right? If I'm pouring out the water, obviously it is going to flow immediately along the surface. But on the other side, if I'm pouring out the honey, this kind of the layers will form, and slowly it will try to flow along the surface. Now, what is an actual difference between these two examples? One fluid is highly viscous as compared to another one. Dabur honey is highly viscous as compared to water, right? So in this case, there exists a kind of a resistance, right? Sometimes fluid itself resists its own flow, as because it is highly viscous. That property, it is known as viscosity, and it acts in terms of a force that is known as viscous force. Suppose if I'm talking about a Dabur, right, it is forming lots of layers like this way. Actually, it was flowing with some velocity, but as because of the property of the internal resistance, some layers are formed like this way, right? So here, the viscous force, right, the viscous force, extremely sorry for this, acting is directly proportional to the area of the cross section. Higher will be the area of cross section, higher will be the viscous force, first part. And second, the viscous force, right, F, is directly proportional to the velocity gradient, the decrease in the velocity with respect to the layer. So F is directly proportional to area into dV by dx. Removing this proportionality sign, we are having the eta A, right, dV by dx. This eta, it is known as coefficient of viscosity. Coefficient of viscosity. Here actually negative sign appears. This negative sign shows it is resisting its flow, right? Fluid's flow. So indirectly the viscous force is nothing else but a measurement of resistance, right, to the flow of fluids. This is actually is all about. Sometimes in some of the cases this right force is also compared, right, to the static frictional force, right? Now Stokes law, right? What does it states? It's a very simple thing. See, we are not moving on to the that much right. See, we are whatever it is needed from the exam point of view, we are covering through all of those stuff. Else to complete this entire lecture in this much amount of the time, it is quite difficult, right? As you all are, right, as you all know, to complete this, right, because it's contained lots of things, but whatever, right, the important topics are there, right, from the weightage point of view, we are covering all of those stuff, right? So don't get worried, whatever things will come after this series, right, we are going to see that into the details also. Don't get worried, but according to the exam point of view, from exam point of view, right, whatever the things are going on, we are covering it fully. Stokes law. Whenever a small spherical ball, it is dropped inside the capillary tube into the liquid, one drag force is acting that will try to resist this flow. When a spherical ball is dropped inside the fluid, when a spherical ball is dropped inside, right, the fluid, when a spherical ball is dropped inside the fluid, right, one drag force is acting. That drag force, right, tries to balance all the vertical forces so that, right, this particle can move with the constant velocity into the downward direction, that is terminal velocity. But what actual the Stokes law is? The presence of this drag force is the Stokes law. That drag force, right, okay, is directly proportional to, right, radius of the capillary tube V, right. Finally the equation is 6 pi r eta V, right, 6 pi r eta V, and using the terms, this is the drag force, this is mg, right, okay, by and in upward direction. So in this case we are having, right, the equation of the terminal velocity is 2 by 9, right, r square g rho minus rho 0 by eta. Okay, so it's all about whenever the particle is dropped. You can see in this visualization, when the particle is dropped from the top height, right, it will try to move with the constant velocity, as because of all, see, net acceleration in the y direction 0, it means that doesn't mean the object is stationary. It means all the y forces are balanced and object is moving with the constant velocity. That constant velocity, it is the terminal velocity. So Stokes law is all about that drag force, and this is another equation of the terminal velocity, right? Let's move on to questions related to it. Two small, see, in Odisha 2000, in NEET 2019, this question is asked. Two small spherical metal balls having equal masses are made from the materials of density. Two spherical balls are there, right? One it is of density rho 1, second it is of density rho 2. There is a relation given rho 1, that is equal to 8 rho 2. One is having the radius of 1 mm, right, and second that is having the radius of 2 mm. They are made to fall vertically in the viscous medium whose coefficient of viscosity is eta and whose density is 0.1. Okay, fluid density, density of the fluid, right, it is of first, that is density of 0.1 to the density of fluid. The ratios of the terminal velocities will be what? It's a very simple thing. What is an equation of terminal velocity? 2 by 9 r square g rho minus rho 0, right, whole divided by eta. right? Viscosity is constant, G is constant, 2 by 9 is constant. So it means simple, the terminal velocity is directly proportional to r square rho minus rho 0. So simple, v1 by v2, right? That is r1 square by r2 square, that is rho minus rho 0, 1, 1, right? Whole divided by rho minus rho 0 of 2. Replacing all of those values given, right? We are replacing value here, this value, right? This value and this value, right? We are getting the equations, the ratios of the terminal velocity is 79 by 36. Right? The D is the perfect answer for this specific question. The direct question based on the terminal velocity. The concept of the terminal velocity, Stokes' law states particle is dropped, right? One drag force is acting, that is Stokes' law, and that is determined by 6 pi r eta v. But when the particle is dropped, right, with respect to that, when the particle is dropped, all of those vertical forces are balanced, right? And it is moving constant velocity inside the fluid, and it is covering the depth. The velocity with which it is covering the depth and all the downwards and upward forces are balanced, right? That velocity is defined as the terminal velocity. In that case, the acceleration, the net acceleration in the y direction is completely zero. A small sphere of the radius r falls from the rest. See, NEET 2018, the question on the viscosity, viscous force has been asked. The small sphere of radius r falls from the rest in the viscous liquid. As a result, heat is produced. The rate of the production of heat, when particle is dropped, the object is dropped, heat is produced. What is the rate of the heat? That is power. Can I say that is force into velocity? Rate of heat, that is power, right? The rate of heat when sphere attain its terminal velocity is proportional to, simple. Rate of the production of heat is force into velocity. Force, it is defined as 6 pi r eta v into v. Can I say it is 6 pi r eta into v square? Here we need to calculate the rate when it attains terminal velocity. It means here v is the terminal velocity. If it reminds us, can I consider this as equation number 1? If we are recalling the equation of the terminal velocity, then v is directly proportional to r square. It means the rate is directly proportional to r to the power 5. C is the perfect answer for this specific question. C. NEET 2018. Now, let's move on to the last topic of this chapter, that is rise of a liquid into the capillary tube, and even rise of the liquid into the capillary tube and the concept of the surface tension. First of all, let's move on to the surface tension. What actually the surface tension is? What actually the surface tension is? I'm giving you all one simple example. There exists a situation in which, right, there exists a situation in which the fluid tries to adjust itself into the minimum surface area and acts like an elastic membrane. A situation at which the fluid tries to adjust itself in minimum surface area and it acts like stretched elastic membrane. This property is known as surface tension of the fluid. Best example. Have you ever kept this cloth wet? Right? Have you ever kept this cloth wet? Yes. Whenever you used to wash up this clothes, we used to do like, generally the boys used to do like this way. Right? Okay. they used to do you like this way. So whenever you are just stretching this object now, right? Okay, the water on the surface of this object will try to adjust into the minimum surface area. Right, at that position it acts like a stretch elastic membrane. Have you ever seen the last drop that is falling from the leaf? It tries to adjust into the minimum surface area and it falls. At that last moment it acts like a stretch membrane. That is the concept of surface tension, and it is defined as force gradient or force acting per unit area. This is what actual the concept of the surface tension is, right? And with the concept of the surface tension, obviously we are going to see, right, some of the important theories, right? Okay, what actually it states, let's see this. Okay, to understand the concept of the surface tension, we are having the equation of the soap bubble theory. Suppose, as because of the surface tension, right, the fluid is trying to adjust into the minimum surface area and it stretches like an elastic membrane. Suppose if I'm talking about a water drop or a drop of a fluid, initially the radius was r. When it acted like a stretch membrane, its radius increased to, right, its radius increased to delta r. Right. So here we are going to define one new thing, right? So here, initial area, that was 4 pi r square. Final area, can I define it as 4 pi, right, r plus delta r whole square? What will be into change in area? That is equivalent to right, 4 pi r plus delta r whole square minus 4 pi r square. So change in area, I can define it as 8 pi, right, r, okay, delta r. If change is quite small, right, can I define it as dA, that is equal to 8 pi, right, r dr. If change is quite small, if change is quite small, I can define it as dA is equal to 8 pi r dr. Right. Now, as because of some pressure difference inside and outside the soap bubble or a drop, let us consider the example of a drop first. As because of some difference, pressure difference, the soap is getting expanded and trying to, it's acting like a stretch elastic membrane. So see, the change in area is this. Now how much amount of the work is done, right, in increasing this surface area is our extra energy. So that work done, we can define it as T dot dA, right? And this dW, I can say T dot 8 pi r dr. Can I consider this as equation number 1? This, right? Now how much amount of the force it is needed? The same. See, suppose if I'm talking about dW is equal to F dot dr, this force that is equal to pressure into area, so it will be 4 pi r square into pi minus p0 into dr. Can I consider this as equation number 2? Yes. Comparing 1 and 2, we are getting the pressure difference between the inside and outside the soap bubble, right? That is pi minus p0 is equal to 2t by r. It is having one free surface, that's why it is 2t by r. If I'm talking about a bubble, then it is having the two free surfaces, then pi minus p0 is 4t by r. This is what an actual derivation of soap bubble theory is, right? As because of this pressure difference, it is going to try or adjust itself into the minimum surface area and acts like a stretch membrane to show the surface tension. The same concept help us understanding the concept of the capillary action. The rise of the liquid into the capillary tube. Let us take an example to understand this. Suppose, Okay, one capillary tube is dipped inside a fluid, right? Okay, and before moving on to that, right, the small definition like what actual the angle of contact is, right? You all are aware of what actual the concave fluid is, what actual the meniscus, concave meniscus, convex meniscus, right, which is a wettable liquid. Okay, you all are completely aware of it. So rise of the liquid into the capillary tube. Let us take an example, right, to understand. Suppose there is one container in which, right, this capillary tube is dipped, right, and this rise of the liquid happens, right, and this phenomena, it is known as capillary action, right? It is known as what? Capillary action. Okay, this is known as what? Capillary action. This rise of liquid occurs as because of this pressure difference. Suppose initially this was the height of the liquid, and after the capillary tube is dipped, it rises up to height h. So rise of the liquid occurs, right, as of the pressure difference. So can I consider pressure difference Pi minus P0 as rho g h, right? And according to our previous theory, right, if meniscus is formed at this capillary tube, then it acts like a stretch membrane, right? See, if meniscus is, right, acting, then this will be your angle of contact, right? Okay, this will be your angle of contact, and we are having the curvature, right? Okay, we are having the curvature for this meniscus. Right, so can I compare this rho g h as 2t whole divided by r? Okay, so comparing this two equation, I'm getting rho g h, that is equivalent to 2t by r, where height of the liquid into the capillary tube is 2t r by rho, so 2t by rho g r. If meniscus is not formed, then we are having this equation. If we are having the respective meniscus, right, with which angle it is there, then we are having 2t cos of theta by rho g r. More will be radius, less will be the rise into the liquid. Less will be radius, more will be the height. More will be the radius, less will be the rise of the liquid into the capillary tube. Less of the radius of the capillary tube we are having, more will be the rise, right? Okay, and angle of contact and these things you are completely aware of, right? So we saw, right, this concept of the surface tension. With that we saw the concept of soap bubble theory, the derivation of it, and the rise of the liquid into the capillary tube, that is a capillary action. Now let's see, in the 2013 sums on this has been asked. The wettability of the liquid depends on which drop of the liquid is going to wet the surface. Who is going to define? Angle of contact. What actual the definition of angle of contact is? It states that angle made by liquid with surface, right? Angle made by liquid with surface, this is angle of contact, right? This is non-wettable liquid, this is a wettable liquid. Example of wettable liquid, that is ink, and water, non-wettable mercury, best example. Meniscus, in meniscus this there is a difference. While moving on to the definition of angles of contact, we are calculating like this way, but in meniscus, right, in the case of capillary tubes, angle is calculated with respect to the wall of the tubes, right? And in that case it differs. Obtuse become acute, acute becomes, there is a difference of the theory, but that thing you all are aware of and you need to remember. So here the answer will be the angle of the contact between the surface and the liquid. Capillary tube of the radius r is, say in NEET 2020 this question is asked. Capillary tube of radius r is immersed inside the water and water rises it into the height h. Mass of the water in the capillary tube is 5 gram. Another capillary tube, see, R1 is R, R2 is 2R. M1 is equal to 5 gram. M2 will be what? Simple. The mass of the water, okay, will be what? Okay, the mass of the water. See, if it reminds us about the formula, let's see on this. The rise of the liquid into the capillary tube. What actual the formula is? This one. 2T by rho gr. Height of the liquid is 2T by rho gr. Can I use this equation? 2T by rho gr, right? The rise of the liquid into the capillary tube. What is mass? Is density into volume, right? Okay. So this mass, density into area into height, right? So can I say mass is directly proportional to r square h, right? So can I say m1 m2, that is r1 square h by r2 square h, r1 square h and r2 square h. Radius of the first is r, radius of the second is 2r, right? M1 is 5 gram, second is, right? Okay, so here by resolving this, right, okay, we are getting, okay, r square, area is r square into h. Okay, 1 r of this we are having, Anna. If we are replacing this h, another r we are having. So m1 by m2, so that will be equivalent to what? Right, r1 by r2. 1 r will be, see, if we are replacing this term, then 1 r will get cancelled, right? So final m1 by m2, right, that will be equivalent to 1 by 2. So m2, that will be 2 into 5 gram. So m2, that will be equivalent to 10 gram. So mass in the second capillary tube is a 10 gram in NEET 2020, just a year back. This question I'm giving you is a question of the soap bubble. I'm giving you all into the homework. You can do it by yourself, right? Okay, this has been asked in NEET 2019. Okay, so guys, this was all about. Let's revise this stuff, right? I'm going to use this thing. Okay, from the beginning, let's see what we have seen into the solids and fluids. The most of the important topics we have covered, right? We have moved on to the Hooke's law, right? Its slope. We have seen the stress-strain curve with an example, elastic potential energy, relevant formulas. We have seen the combination of rods, thermal stress. We have seen some sums related to it, right? And after that, we moved on to the concepts of fluids, right? After that, we moved on to the concepts of fluids, right? And the Pascal's law in its respective application, right? And pressure at the depth. Okay, this all of these applications of Pascal's law, right? Okay, and after that, slowly we moved on to the Archimedes principle, law of flotation. Some of the cases we saw, right? Cases with an exception, right? We saw. Okay, and after that, slowly we moved on to the equation of continuity, its relevant sums, right? Bernoulli's equation we saw, right? And after that, its derivation and some of the applications like venturimeter, Torsley's law, velocity of efflux, and its relevant sums we saw, right? And I've given you all some homeworks, viscosity, Stoke's law, right? And the relevant sums with the surface tension and the rise of the liquid, soap bubble theory, the rise of the liquid with angle of contact into the capillary tube, right? Okay guys, so right, Reynolds number, types of flow, the small things are remaining, but those things you all are aware of. I have taken the past 5 to 7 years PYQs and I've seen the most important theories according to the weightage and I've presented in front of all, right? So don't worry, things will come upon. Okay, it's time to go and end this session, right? So this is Indrajeet Singh, guys, signing off from the desk. Again, we will move on with the heat transfer, come back with the heat transfer with the awesome teaser and the thermodynamics, right? So this is Indrajeet Singh signing off from the desk. Students, bye bye. Sat Sri Akal and namaste from my side, Bacha ji. Bye everyone. Stay at home, stay healthy, stay care. MSD pandemic. Bye everyone.